Hello, everyone, and welcome to the fifth annual International Mission to Mars Design Engineering Competition. Today we have day three, defense. First up, we have Nova Lab, and I do want to mention that if you were um, critiqued by another team for using AI, the list is here on the screen. Please be prepared to defend that critique. And first up, Team Nova Lab, you have the floor. You're muted too. You have
Okay.
20 minutes.
Do you hear me?
Yes.
Okay, thank you. Wait a minute. Um, okay, yes, okay. Okay, hello everyone. Today is finally the last day, and we have all put our absolute the best effort into this journey, no matter what the final result will be. I would like to congratulate all the teams here. Everyone has worked so hard and done an amazing job with full dedication. Today, our team Nova Lab is ready to share our final presentation and answer your question. Okay, Q&A. Next, please. Regarding your landing site, why did you choose Elysium Planitia, and how can you prove that the lava tubes are accessible in practice? Okay. Um, First, as you can see on the slide, we have already set the exact coordinate for our landing site. We choose the Elysium Planitia because it is low-lying plane. This means the air is thicker, which helps slow down the spacecraft safely during landing. If we want the mission to succeed landing, we must be safe first. Yeah, first step. This site is highly secure and has already been proven by NASA InSight mission. According to NASA, Elysium Planitia has just the right surface for the instrument to be able to probe the deep interior, and its proximity to equator ensure that the solar-powered lander is exposed plenty of sunlight. Second, regarding the lava tubes, we obviously cannot run light inside or on top of lava tube because that would be too dangerous for anyone. Instead, we choose a safe area nearby, close to Elysium. Study showed that the volcano erupted around 53,000 years ago. In geological time, this is very recent, therefore, it is highly possible that chemical and biological traces still remain there for us to study. Or we call this tube is a Elysium month. Okay. Lastly, to those who say exploring this tube is impossible in practice, NASA is already developing the robot to explore this exact area, and they are close to success in the beginning. We do not need to risk human life by going in first. Instead, we will use a swarm to scout robot and drone to enter the explored lava tubes before our crew follows. Okay, yeah. Next, next. Martian soil contain high amount of toxic percolate. How can your project grow plant without feeling like in the movie The Martian? Okay, next. Regarding the Martian soil and percolate, yeah. You are absolutely right that soil is highly toxic and cannot plant anything directly into it. However, we are not doing what they did in the movie The Martian. We have a clear scientific plan for soil remediation. First, we will use a bioreactor with a specific bacteria called Dendroromonas agitata. I hope I pronounced correctly. This bacteria safely break down and toxic perchlorate into harmless chloride and pure oxygen gas, so we clean the soil and get extra oxygen at the same time. After removing the toxins, we will adjust the soil pH level, wash away excess chemical, and mix it with a safe biofertilizer. Science has already proven that plants can grow in Mars, like soil, once it is treated and mixed with organic nutrients. We are transforming dead space dust into living, healthy soil. Okay, and for this question, next. Next again. A normal transparent dome will fill under high internal pressure and will be covered in Martian dust. How does your structure solve this engineer challenge? Okay, we are so prepared. Let's dive into the core engineering of our habitat. We have integrated advanced mechanics to solve the stress, dust, and radiation issue. First, regarding internal pressure, a former dome will fail due to high hoop stress. To solve this, we use a geodesic truss system to convert the tensile stress into axial compression. For the transparent panels, we use ALON or aluminum oxynitride. It is a transparent ceramic with a tensile strength of 300 megapascal. Okay, sorry. It perfectly contains the 1 atmosphere of internal pressure and resists dust abrasion. Second, to prevent the dust blocking sunlight, we use a NASA EDS technology. We embed microconductor inside the outer ALON layer. By applying a three-phase AC signal, it creates a traveling electrotechnic wave. This wave uses the electrophoretic force to continuously lift and push Martian dust off that curved structure. No human cleaning is required. Finally, regarding early phase radiation protection, we are not waiting for our microarchitecture to grow. Our dome used the double wall water branch system filled with a 50 centimeter layer of liquid water. Because water has a high density of hydrogen atom, it acts as like moderator to attenuate galactic cosmic ray and prevent secondary radiation from day one. This is solid multiple layer physics and engineer solution. Okay, next question. Your schedule give more than 2 hours per day for meal. Isn't this is a waste of mission time, and how to protect the crew maintain from isolation? Okay, wait a minute. Okay, about the schedule time. Okay, regarding the crew schedule and lunch time, I would like to clarify our physiological strategy. The 2 hour allocated for meal each day is not waste of time. Instead, physiological. This is called social dining. Astronauts on Mars face extreme isolation, right, and high stress. Eating together is not just nutrition. It is a critical tool to build team unity and reduce loneliness. Group dining allows the crew to talk, laugh, and support each other, which prevent mental burnout and maintain high performance for critical mission tasks. To protect their mental health, Our schedule includes mandatory downtime and team activities. We have structured gaming session and virtual reality experience to help you feel relax and escape the stressful environment. Furthermore, to prevent the feeling of isolation from the Earth, our ground support team act as a human operator. Yeah, they carefully filter and update the crew with positive news and message from home every day. This keeps the team connected to humanity without overwhelming them with the bad news that cause anxiety. Every evening, the crew will participate in the mandatory group check-in and behavior alignment session. This is a safe space where team members can openly share their stress, solve conflicts, and support one another by addressing mental fatigue and adjusting attitude daily. We ensure the team remain emotionally stable and united throughout the one-year mission. Okay, next question. Looking at your slides, did your team use AI to generate the presentation image and content, and does this violate the competition rules? No, we absolutely did not use AI to generate all content or slide. However, we deeply apologize if some part of our presentation seem to lack deep information or research reference. We had a very limited time to prepare this slide because our team is currently facing in midterm exam in our country, which made it difficult to prepare as perfectly as we want. Regarding the visual or image used in presentation were taken directly from Google, and all data comes from various research or website. Okay, so did we have any more question? Next slide. Okay, we would like to truly thank you everyone for listening and giving us so many valuable comments. For the part where we made honest mistake, we accept them, really accept. And for the part where we have solid evidence to defend our project, we have already explained them to everyone clearly. I hope it. Thank you everyone for listening. Thank you very much.
Thank you. Very good job on the defense. The next team will start in 5 minutes. Is the next team in the room? The next team is AD Mars Pioneers. Is anyone here from that team?
Yeah, I think I can see you, Mikkel Zoom and Ms. Gunera there. So I don't know. Mikkel Zoom, or you guys can start.
They can start in 5 minutes.
Okay.
Okay, 5 minutes. We'll be. Your 20 minutes starts now. If you are talking, I cannot hear you, and let me know if your team will be presenting.
I can see them there, but let me check what's going on.
Do you want me to play the video you sent?
Let me just check with them first. Right. Thank you. I am gonna share their slides and she can, I think, actually.
Go right ahead.
I am Ume Gulsum. I am from Team AD Mars Pioneers. I am going to answer of questions raised against our presentation. Show first slide, please. Thank you for your constructive feedback. We appreciate your observations and would like to clarify a few points. First, regarding Martian rocks and minerals, our objective was to introduce the major geological features that support the scientific value of our mission. We intentionally focused on the broader geological context rather than discussing individual rock types in detail. Since our mission included multiple sections, we aimed to provide enough scientific background to justify our exploration objectives instead of giving a complete geological analysis. Regarding the presence of water on Mars, our purpose was to establish that Mars once had conditions that may have supported life, the detailed processes behind atmospheric loss, and the disappearance of the magnetic life field are part of planetary evolution, which is a separate scientific topic. We mentioned the existence of ancient water because it directly supports our mission objective of searching for evidence of past habitability. Next slide, please. We would like to respectfully clarify that several environmental conditions were already covered in different sections of our presentation. In the Mars environment section, we explained the thin atmosphere, low gravity, dust storms, and the average surface temperature of around -60 degrees Celsius. Radiation was discussed later in our health and human adaptation section, where we explained the use of regolith shielding, personal radiation monitors, and a protected radiation shelter. We also addressed communication delays in our Mars technology section. Our presentation was intentionally organized so that each topic was explained in the section where it was most relevant rather than presenting all environmental challenges together. While we did not specifically discuss percolates, our focus was on the environmental factors that directly influenced our mission design, astronaut safety, and engineering solutions. Regarding the magnetic field, we acknowledge that the loss of Mars' magnetic field is one of the reasons the planet lost much of its atmosphere. However, our objective was not to explain the complete geological evolution of Mars. We mentioned the presence of ancient water to establish the scientific basis for our mission and the possibility of past habitability. A detailed explanation of magnetic field loss and atmospheric escape is an important topic in planetary science, but it was beyond the scope of the background section of our presentation. Next slide, please. Thank you for your question. We would like to clarify that our presentation did not specifically adopt a two-launch strategy. So this concern is based on an assumption rather than our mission design. However, regardless of the launch architecture, crew safety remains our highest priority. Before astronauts begin surface operations, all critical systems, including the habitat and life support systems, would be fully deployed, tested, and verified to ensure they are functioning correctly. If any critical system failed to operate properly, mission activities would not proceed until the issue was resolved. This verification process is an essential part of ensuring a safe and successful Mars mission. Next slide, please. We would like to clarify that our mission did not rely on a single engineer. Our crew consisted of a mission commander, a systems and engineering officer, a science and research officer, and a medical and life support officer. Each member had clearly defined responsibilities, so the mission was not dependent on only one person. We assign primary rules for clarity, but that does not mean the mission relied entirely on one individual. Our presentation was intended to provide a mission overview rather than a detailed reactor engineering design. The purpose of introducing the nuclear reactor was to explain how continuous power would be maintained on Mars. Detailed reactor specifications such as landing mechanism, thermal management, and exact power output fall under the engineering design phase rather than the mission design presentation. We would like to clarify that radiation protection was included in our presentation. We explained that the habitat would be covered with Martin regolith to act as a natural radiation shield. In addition, astronauts would wear personal radiation monitors, radiation sensors, would continuously monitor radiation levels, and a protected radiation shelter was including for solar storm events. We would like to clarify that our presentation did include an emergency shelter in the safety and emergency procedures section. The emergency shelter is integrated within the habitat so that astronauts can reach it immediately during a dust storm, radiation event, or any other emergency without exposing themselves to the external Martian environment. Our focus was on explaining its purpose rather than describing its exact internal location. Next slide, please. Next slide, please. Launch window. By the 26th month, we meant the approximately 26-month launch window that occurs because Earth and Mars align in the most favorable positions for interplanetary travel. This is standard concept in Mars mission planning, and our intention was to refer to this launch opportunity, not the literal 26 months of the mission. Landing site. We would like to clarify that our landing site was presented in a separate slide. We selected Arcadia Plancia and explained why it was chosen, including its underground ice deposits, relatively flat terrain, suitability for safe landing, and its potential for future human settlement. We also explained that the landing area would be scanned using cameras and sensors before touchdown. Next slide, please. The presentation focused on general facts about Mars instead of engineering defense. The introductory section provided scientific background to explain why Mars is a suitable destination. The engineering aspects were present in later sections, including the habitat designs, life support systems, power system, ISRU, communication systems, rover operations, drilling technology, and safety procedures. Our presentation was intentionally structured to move from scientific context to engineering solutions. Surface scanning system was mentioned but not explained. Defense. We explained that the spacecraft would use cameras and sensors to scan the landing site and identify hazards before landing. In addition, autonomous drones would create 3D maps and identify safe routes for exploration. Our focus was on the function of the system rather than its internal engineering design. Water-based exercise was not explained. We would like to clarify that our presentation did not purpose water-based exercise. We explained that astronauts would use a treadmill, a resistance exercise machine, and a stationary bicycle to maintain muscle and bone health in low gravity. We would like to respectfully clarify that the extraction and purification process was already included in our presentation. We explained that underground ice would first be detected using scientific instruments that extracted with a drilling machine, melted in an ice melting unit, filtered and sterilized using a UV purification system before being stored for drinking and other uses. Therefore, our presentation did explain both the extraction process and how the water would be made safe for human consumption. Next slide, please. Thank you.
Thank you for your wonderful presentation. Is anyone else from your team going to present today?
I don't think, I think they're done. Is that right?
Okay, the next team will be starting in 7 minutes. Elena, Anya, Sophia, Sharar, Zohar, and Sakshi, are you here? Mars, let's see, the MISA project. If you are here, you will start now in 6 minutes. Go right ahead. You have 20 minutes.
We would like to thank everyone for the constructive criticism and feedback we have received on with the aim to make our presentation better. With that in mind, we have broken down all the feedback we received and hopefully close out any concerns that were given. Firstly, our first concern was our instruments we were using for our scientific values. For our geology, we will use a rotary percussive drill, an X-ray diffraction fluorescence, a specific brand with Chemin, I hope I'm saying that right, that NASA used, and then Sherlock that was also used to do is a spectrometer that will go through organic compounds, and RIMFRAX, which is a penetrating radar that NASA also used. For climatology, we'll use EMIDA, which is a weather station, and it's attached to a NASA rover, which will be able to conduct to measure and mastering weather conditions, atmospheric pressure, wind pressure, and everything as a sort. Then we'll also use a sample analysis, which is a bunch of scientific instruments that NASA tested on its rover, and it'll analyze gases, rocks, soils, and anything else to be able to study the composition of the atmosphere and surface on Mars. For paleontology, we'll be using Sherlock, which was mentioned in geology, and a scanning microscope. This helps us examine the rock microstructures, which have potential to resemble fossilized microbial, to help us understand what was on Mars before and what could be used now. And for astrobiology, we'll also be using SAM and a gas chromatograph, and that will detect organic compounds. And when I was conducting an interview with Ravi from NASA, he said to use DNA or RNA style life detection, and that's in its experimental phase right now, but it's a search for organic chemistry and potential biosignatures. One of the questions we were given is how would scientific findings contribute to the future human explorations? By exploring Mars and taking back samples, we will be able to identify safe locations, valuable resources, and best solutions best solutions for engineering long-term human exploration. We'll also be able to understand Mars' geology, climate, water, past life, and make sure that future missions can become more safe and sustainable. How would scientific findings contribute to the future human exploration? For construction, Martian rocks and minerals can be used to build habitats, roads, landing pads, and so on. Radiation, we can use layers of Martian soil and rocks to shield habitats, especially in lava tubes, which reduce astronauts' exposure to radiation. Finding clay and certain minerals can indicate where water may have existed or where ice deposits may be located. Minerals can also provide useful materials such as metals, silicone, and oxygen for construction, electronics, and life support systems. Certain Martian minerals contain oxygen that can be potentially extracted for breathing and rocket fuel. All information on this slide and the slides previous were from a mix of research and an interview with Captain Mohammed, who is a chairman at Mars UAE. Avoiding contamination. We will use sterile tools and containers containers and clean and sterilize each tool before collection. We will store samples in an airtight container to prevent contamination and to maintain quality. As stated in our presentation, we will label each sample container with location, date and time, and where it was collected. We will also include a depth detail and the environmental conditions it was collected in. By depth detail, we mean how far did we collect it down. And we'll also limit human contact by using robots to ensure lack of contamination. As stated again, there will be experiments on Mars, but after the astronauts go home, there will be further experiments as well as comparing our findings to components on Earth. One of the questions brought up was robots and what would they do? The robots will be doing all the heavy lifting, moving materials and basic assembly, alongside managing excavators, drilling and setting up base. We will also have rovers that are adapted to operate without human control and make them do most of the research on terrain. The robots will be in the first launch and will be independently setting up base and carry out any tasks before the crew arrive. They will also maintain the structure of the base, fix any damages, clean any dust buildup and more. The robots will be used to make up for a small crew size and do any extraneous tasks. We will be using technology to do the bulk of the work because robots and drones can work for 24 hours, do not need water, do not need oxygen, and they do not need sleep. Our astronauts will maintain the technology during this stay on Mars. How to battle radiation. When our crew members are outside, their spacesuits will be covered in a BNT fiber, which is radiation resistant. Activities will be limited in high levels of radiation, and we'll have shielded rovers will be used for long trips. We'll also carry radiation detectors when going out to monitor the levels. Inside the habitat, there will be thick shielding from water, soil, or Martian materials around the living areas. We will monitor radiation levels inside with sensors and alarms. And we'll use extra materials such as regolith, water, and storage around living areas for extra protection. The habitat will also be deep inside lava tubes for better protection, and natural rock will help shield from radiation too. For the greenhouse, we stated that we will grow tomatoes, potatoes, carrots, and lettuce while on Mars. Reasons were stated on page 32 of the presentation. As well as studying how gravity will affect plants on Mars, we also stated how we will study how radiation affects the plant growth, how the plant will grow without any soil, and how artificial light can affect and will there be a difference in taste. In terms of hydroponics, the plants are grown without Martian soil using water. Water is recycled and reused to reduce waste. Sensors and AI will control nutrient, temperature, and plant health, and will also create a closed-loop farming system for sustainable Mars habitat. The LED lights will also provide energy for photosynthesis inside the lava tubes. For water recycling, wastewater for showers, washing, and hygiene is collected and filtered. Urine and moisture from the air are processed to recover usable water. Plant and hydroponics is also collected, purified, and returned to the system. We'll have sensors to monitor water quality to ensure it remains safe. Advanced filters remove impurities, chemicals, and bacteria. Waste management and medical support. For waste management, we'll have organic waste such as food scraps and plant waste, and it is processed into nutrients or fertilizer for our farming. Human waste is treated to recover water and valuable nutrients while preventing contamination. Carbon dioxide from astronauts is captured and used by plants for growth. Hazardous waste is safely stored and processed separately, and we'll have monitoring systems to track waste levels and recycling efficiently. For medical support, our crew members are trained in first aid, surgery support, and emergency responses, and will have emergency supplies for each response. We'll also have a quarantine area which can isolate crew members if needed. Communication with Earth doctors provides additional support, even if there is a time delay. Every support is needed. The habitat also has a backup power and life support systems to keep medical equipment running during emergencies. All these informations were on recycling and medical was conducted during an interview with Dr. Ravi, who works for Mars and assisted in multiple launches. For power systems, I stated we'll be using solar power as our primary, nuclear as our secondary, and battery power. From following the critiques, we have decided to combine nuclear and solar together, so if one fails, the other one will continue. For energy consumptions, our largest energy consumptions are life support systems, hydroponics, heating, water recycling, and our robots. Our oxygen production and CO2 removal, our astronauts will produce carbon dioxide when breathing. The carbon dioxide will be removed using filtrations, and then the captured CO2 is sent to hydroponic farms where the plants use it for photosynthesis. Plants can also release oxygen, which will support in the habitat's atmosphere. For training, we stated we'll use multiple environments for our crew, but the best environment will be the desert because it resembles Mars with dry landscapes, extreme temperatures, dust, and limited water availability. Mountains and wilderness training develops navigation, teamwork, and survival skills needed if astronauts must operate away from their main habitat. We have also stated that the crew will train in large underwater pools with weights on their ankles to get them used to the weight of the spacesuit when walking. Medical training and system repairs. Astronauts will learn first aid, emergency medicine, and injury treatment before immediate help from Earth, because immediate help from Earth is impossible. Training includes treating fractures and wounds, managing burns or illnesses, and performing CPR. They will also be taught how to use medical equipment and diagnostic tools. They will also be responding to emergency during EVAs. All our crew members are trained to support each other and use medical systems for diagnosis and guidance. Although there is a medical officer as part of the crew and will have more medical training than the others due to their profession, we would like all members to have one in case anything happens during expeditions. Although the robots will do most of the work, such as repairs, and the astronauts will be trained to repair critical habitat and spacecraft systems, which include the life support systems, water recycling systems, power systems, communication systems, and habitat structures. The rover will be using a closed-loop life support system similar to the spacecraft. There will be CO2 scrubbers to remove carbon dioxide from astronauts' breathing air. There will be sensors continuously monitoring oxygen levels, air pressure, and air quality. Emergency oxygen reserves provide backup if the main system collapses. And our evidence is that NASA's rovers such as Curiosity and Perseverance, redundant systems, radiation-resistant electronics, and thermal testing. And the question about our yearly checkups will be based on Mars years, which would be every 2 years for Earth years. Thank you very much. We finished.
Wonderful presentation. Thank you so much. Our next team will start in 9 minutes. Is the next team here? George, Pavel, Ismet, etc.
Yes, we're here.
Perfect. We will start in 9 minutes. See you then.
1 second, let me just share my
You-
screen.
You have the floor.
Thank you. So, where is it? Okay, so we are Team Red Horizon, and these are our final arguments. Here are the critiques we got. We are starting first with the habitat radiation and ice thickness. Ismet, please.
So, hi, I'm gonna answer the question about that has been given to us. The question is, your habitat relies on an ice jacket radiation shielding system. Will you provide its thickness, and have you calculated the radiation shielding? So our jacket is about 2-3 meters thick around the habitat. We made it that thick because ice water is really good at blocking radiation. It has got a lot of hydrogen in it, which slows down neutrons and blocks gamma rays and cosmic radiation pretty well. We based the thickness on some published NASA studies about water shielding, aiming to keep the crew's yearly radiation dose under NASA safety limits. So the calculations are unshielded dose rate on Mars surface. And NASA's Curiosity rover measured Mars surface radiation at about 0.664 MSV per day, which comes out roughly 230 MSV per year unshielded. Mars' thin atmosphere already blocks some of it compared to the space. NASA's crew radiation limits cap total carrier exposure to around 600 MSV. For a multi-year mission, they keep the dose under 100 MSV per year. So we're gonna need 2.3 times like reduction in dose rate, so it makes around 43.48 MSV. From NASA's shielding studies for the 45-50% dose reduction, we're gonna need 50 plus areal density. To hit our target 2.3 57% reduction, we need to land around 50 to 60 GCM squared of water equivalent shielding. Converting to actual ice thickness, ice density equals 0.92. So thickness equals areal density divided by density, which is 55, divided by 0.92, which makes 59.783, roughly 60 centimeter and about 0.6 meters. That's it. And now Bogdan is gonna answer the second question.
Now moving on to the nuclear reactor, the SR1 nuclear reactor we chose are not currently in production. The SR1 nuclear reactor will be launched with the SR1 Freedom in 2028. The plan is using 3 of them to power everything. The way this reactor works is by using a highly low-enriched uranium. As a regular SR1 reactor will be too heavy for our mission, we have to use the architecture of a kilopower fusion reactor with the SR1. Our plan is similar to the Lunar Reactor 1 that wants to use one of these reactors to power NASA's lunar bases. To move away from flight-rated propulsion to a continuous ground power network, the reactors are adjusted accordingly. A spaceship moves through a vacuum, so it has to carry a massive radiators to get rid of the heat. Because Mars has a cold atmosphere, it works as a natural fan to cool down these radiators. To continuously power the grid, we have to connect these reactors using high temperature superconducting lines to solid state transformers. The two reactors combined provide 60 kilowatts of electricity. It works by using a closed Brayton cycle that uses the system heat to spin a turbine that acts as a generator, providing 10 kilowatts per unit.
So we had another question about the landing zone coordinates. So the question was that they stated that 2 spacecrafts would land about 2 kilometers apart, but the coordinates they gave different by roughly 0.9 degrees latitude. On Mars, 1 degree of latitude is about 59 kilometers. So that difference implies roughly 50 kilometers or more, not 2 kilometers. The second, the landing zone and coordinates. It's true our previous coordinates were wrong. We didn't give the exact coordinates, therefore a 50-kilometer error was created. So the AP1 landing site was correct, like 39.8, negative 157.9. The second launch was wrong and was too broad. The landing spot should be 0.0338 degrees north of the first one, 39.8338 and negative 157.9. The first launch is marked with an orange X and the second launch is marked with a red X.
So the next critique was about habitat pressure and atmospheric conditions. The pressure of our habitat is 14.7 psi. We chose that as the official PDF for the Mars Ice Home habitat from NASA states that this is the best choice. We agree that nitrogen is not really available on Mars. Our approach is to transport the initial nitrogen supply from Earth. For nitrogen replenishment, we would use high-pressure nitrogen tanks. We base this on NASA's NORS concept, which has already been used to transport nitrogen for spacecraft resupply. We also designed the habitat to minimize air leakage, so only small amounts of replacement nitrogen would be required over time. Although we did not describe these details in the presentation, our habitat would use airtight materials and multiple sealing layers to minimize air leakage, similar to modern space habitats. Um, why use high pressure? You might ask, why use high pressure tanks? Why are they useful in this situation? We investigated different methods of transporting nitrogen, including high pressure tanks, liquid nitrogen, and nitrogen compounds. Based on NASA studies, high pressure tanks are the safest and most reliable option.
To the rover and production rates. So for the first mission, the unmanned one, we decided to send 2 rovers. They work by using a direct planning, path planning, which is widely used in autonomous driving. It is true that the rovers are not fully autonomous, but use a semi-autonomous system. The worst scenario possible would be a leak or a Martian dust storm. For these scenarios, we decided to equip the rovers with multiple LiDAR sensors and cameras, as well as an AI system, so they can work even without human intervention. To mine the required water for the fuel, we need 48 kilograms per sol. This means about 2 kilograms of water per hour for the fuel. For our crew, they would need 12 kilograms per sol, but because we are using a 90% effective water recycling system, the rovers actually need to mine around 1.2 kilograms per sol per person. This equates to 4.8 kilograms per sol. If we factor in the hydroponic garden and the fuel requirements, we need around 55 kilograms per sol until the fuel is done. 300 sols with the equipment running every day. After that, it is just 7 kilograms per sol. Now moving on to my teammate Aradna.
I would like to thank you all for taking the time to review our mission. We appreciate all the feedback because engineering is about questioning ideas and improving them. I'd like to respond to the main concerns generally that were raised about our project Red Horizon. Firstly, there was a question about our landing geometry. It was pointed out that our coordinates suggest a much larger separation than the 2 kilometers we mentioned. We acknowledge that this is a presentation error on our part. Our intention throughout the mission design was for both landing sites to be approximately 2 kilometers apart so that the crew could easily travel between them while still maintaining a safe distance in case one landing experienced an unexpected problem. The incorrect coordinates do not reflect our intended mission plan, and if we were revising the presentation, we would correct those values to match the logistics we described. The next concern was about our habitat atmosphere. We chose an Earth-like atmosphere because one of our main priorities was protecting the astronauts' physical and mental well-being during a mission lasting several years. Living in an environment that closely resembles Earth's atmosphere reduces psychological stress and allows astronauts to work more comfortably without constantly adapting to different oxygen levels or pressure changes. It is true that maintaining this atmosphere requires a large amount of nitrogen, and we could have explained this in more detail. Our mission assumes that most of the atmospheric gases are delivered during the first unmanned cargo mission, which carries the habitat and heavy infrastructure before the astronauts arrive. Since our habitat is designed as a sealed system with airlocks and carefully monitoring gas losses would be relatively small, meaning nitrogen would not need to be replaced continuously. While lower pressure habitats are certainly a realistic alternative and are used in many mission concepts, we chose an Earth-like environment because we prioritized crew comfort and long-term habitability. Another criticism was that our robotic preparation relied too heavily on instructions from Earth rather than operating autonomously. We understand why this concern was raised. However, our intention was never for Earth to control every action performed by the robots. Instead, the robots would complete routine construction, excavation, habitat deployment, and system checks independently using pre-programmed artificial intelligence. Daily communication from Earth would simply provide updated objectives, monitor progress, and solve unexpected problems that require human judgment. Because communication delays between Earth and Mars can be over 20 minutes, our design already assumes that the robots are capable of making immediate operational decisions on their own. There was also a question regarding our in situ resource utilization, particularly the production of methane and oxygen for the return journey. We agree that our presentation did not include detailed production calculations. However, the chemical pathway we selected is based on existing scientific research. Water extracted from Martian ice is separated into hydrogen and oxygen through electrolysis. The hydrogen then reacts with carbon dioxide from the Martian atmosphere using the Saboteur reaction to produce methane fuel. This is the same basic concept being investigated by NASA and SpaceX for future Mars missions. Our presentation focused on demonstrating that the overall system was scientifically possible rather than presenting every engineering calculation. If we had more presentation time, we would certainly include expected production rates, storage capacity, and fuel generation timelines. There was also a question about the ice layer surrounding our habitat. We selected the Mars ice home because the ice shell provides two important advantages. Firstly, water is naturally very effective at absorbing harmful space radiation. Secondly, unlike thick metal shielding, the semi-transparent ice allows natural sunlight to enter the habitat, helping astronauts maintain healthy day-night cycles while still receiving radiation protection. Although we did not specify the exact thickness of the ice shell. The concept itself is based on research carried out by NASA, where the thickness is determined through radiation modeling, depending on the mission requirement. Since our project focused on overall mission design rather than the detailed structural engineering, we adopted this proven concept instead of developing a completely new shielding system. Another question focused on our use of the SR1 Freedom nuclear reactor. Our intention was to use a compact nuclear reactor because solar power alone is less reliable on Mars due to long-lasting dust storms. We recognize that the SR1 Freedom reactor is still a conceptual design rather than an operational surface power system. However, conceptual technologies are commonly included in future Mars mission proposals because many of the systems required for human exploration are still under development. Our design assumes that the reactor would be adapted to provide continuous electric power after landing rather than propulsion, allowing it to support the habitat, life support systems, and ISRU equipment throughout the whole mission. Overall, we believe many of the questions raised were not necessarily about flaws in our mission itself, but about areas where we could have explained our decisions in greater depth. Because of time limits, we had to simplify several technical aspects of our design. If we were to expand this project further, we would include more detailed engineering calculations, atmospheric modeling, ISRU production rates, and reactor specifications. Our two-launch architecture reduces mission risk. Our robotic preparation allows the crew to arrive at a functioning base. Our choice of Arcadia Planitia gives us access to valuable subsurface ice, and our use of nuclear power and in situ resource utilization supports long-term sustainability. While we acknowledge that some technical details could have been explained more clearly, we are confident that the overall mission concept is scientifically sound and provides a strong foundation for future human exploration of Mars. Thank you.
And this is everything. Thank you.
Thank you so much. Great presentation. Is Team Sol Epis here? I think I see some of you in the audience. If you are here, okay, perfect. You will start in 4.5 minutes.
Project Terra Firma, Team Sol Elpis, and it's our defense round. Next slide.
There's no sound.
Mm. So, answering to Miasa, all 6 crew members are certified across ECLSS, EVA, and medical response to absorb workload during any crew emergency. Mandatory body system setup prevents critical bottlenecks. Dynamic scaling, secondary scientific tasks suspended automatically to prioritize core base operations. Their critique was about
we bring 75% of the food from Earth, which is around 2.4 tons, and 0.3 tons of water, which eliminates immediate crop yield dependency. The fertility tables are in our presentation that we sent to the judges. The mass buffer we have at around 8.83%, so weight should not be a problem. It is 2.65 tons. Next slide, please. So, Hematheria, if they said our water numbers are over with, I agree, yes, our water numbers are over, but this capacity design helps us fill up our water jacket fast. Also, yes, our backup mission is not has the same philosophy. It is completely different due to completely different power generation. This if early failures should be detected easily, because we said this mission would be launched if the 2027 demonstration of our reactor is successful. If it is not, then it would not be. If we launch and the heat would be enough to melt the ice below. So next slide. Yeah. So Dex Lab 3 questioned about our shielding efficiency, and they said we had no calculations. Here we already have our calculations mentioned in the same slide we referenced to. We have 25 grams per centimeter square of shielding. This is from the water shield we have, and this also is enough according to NASA's TP3079 and TP 2013-217983. Next slide, please. Okay. The team Dow High accused us of using AI, that there is a suspicion of we used AI, but we had not used AI. There are false positives with AI detectors, and we all had written our parts of the report. We have our versions in backup files. And next slide, please. And according to other AI detectors we checked, this shows 0% AI. Next slide. So thank you. This was all.
Is that the end of your presentation?
Yes, ma'am.
Okay, thank you so much. The next team will start in 10 minutes and is the Team DexLab 1 present. Okay, go ahead.
Okay, I'm Hadi Harfouch from the DexLab 1 team, and before going for the critiques, we're gonna have to face the AI allegations that have been circling, mentioned by Team Dohai. I hope I pronounced your name correctly. You said that our file contained AI-generated images, and as shown in all the images, and I'm sharing my screen right now, nearly everything was made by our team, like all the tables, the charts, taken from official sources. You can reverse search all of the images and tables shown. The tables are all from our file, and the images are easy. For example, here is a mission robot that one of the team used. I can simply copy it for Google and reverse image it and use reverse search to find exactly where this this image was extracted or where was it present, because all of our photos that we use that are not made by our team are from public Google, and anyone can actually find them. Now, if your critiques were especially for this photo, where we AI modified our own images, now we can definitely say that's not AI. We did use it actually. But our team wants to make it clear that this is not a scientific critique. It doesn't actually critique anything inside of the presentation. And unless there is some multiple science cards or, I'm sorry, unless there's actual scientific information with our photos in them, we didn't think actually this is anything that should be, I think that we should be disqualified for. And we hope the judging panel would forgive such a small mistake from ours, especially since the person who did it actually didn't realize it was prohibited, since it's our own images. It doesn't actually include any information. We didn't actually use it. Now, for multiple of you watching, you might remember that there was multiple slides shown in their screen sharing while in the critiques, and that's not entirely true. In their screen sharing, they had only 2 slides, our faces, which they made small at the corner, and another slide where we used visualizations. Now, again, we can say this is not AI. We made a mistake. We didn't realize it was prohibited. But this is only 1 slide. And you mentioned that AI is prohibited because it is an unfair advantage. And considering none of the judges would look at those 6 squares and say that, and confidently say that this slide is the reason we're going to win the competition, it's an unfair advantage, no other team could have done anything similar to it, we don't really think that's a scientific critique, especially since the slide is only for the 6 objectives and 2 phases we have, which are also mentioned afterwards. So this slide doesn't really serve anything in the presentation. It was only visualization. And outside of the defense, it's actually a clever idea by you to duplicate this slide twice, make it seem that there's multiple slides, along with our team photo, which, yes, again, it was very small at the corner. We didn't realize it was prohibited. It was at the corner. No one could actually see it. It's not really an unfair advantage. This is not a reason. No team would actually win because their photo was like AI generated. The photo is not scientific. It doesn't include anything. Obviously, it have a dragon. We're not going to send the dragon to Mars. I thought that was obvious. Now, for your official critiques, you had multiple critiques. Now, we made mistakes. Of course, you had us with the launch window. We can't send them 9 months apart. That's true. We're going to have to modify that. But the rest of your critiques weren't as lucky. First of all, you said that we didn't have a mass budget. And I remember watching this back on YouTube, and the subtitles were like, you never show the mass budget. And as shown, I tried to make it as obvious as possible. This is the official Mars Society YouTube page. This is the video. This is all the link. If anyone wants to verify, this is the exact timing at which this screenshot was taken. And you can say that we didn't only have a mass budget table, but we also had a pie chart to visualize the table, making it even more clear. The same can be said for the timeline. You said our timeline was fake, and in the presentation, I remember you said, I quote, murky. And not just did we visualize it with 1, but 2, including, I believe it was called Gaga table, in which we literally said all the dates by day that, at which the mission will happen. They're on the screen. The timing of the video is also on the screen if anyone wants to check. Also, you said that we're going to assume the Insight resource materials will be founded for 3D printing the rover because we're going to 3D print using iron and high density polyethylene. But we didn't assume anything. In fact, it was very clear in the presentation that we had the exact coordinates at which we're going to have these materials. We didn't just assume we're going to Mars, we're going to have liquid water, we're going to have oxygen. We have the exact coordinates and we have the exact machinery to make all of that possible. And all was specified in our presentation. Also, for the HDPE, in case it wasn't very clear, here's an extra visualization that we had. And this is it when it's bigger, showing exactly where we're gonna get it. And we did mention it while speaking that we're gonna extract it and we're gonna use it. So please note that. Now, in response for the Etheria team, first of all, you said that the project timeline was unclear. Again, we addressed that issue. You said that producing iron and high-density HDPE on Mars requires excavation, processing, and substantial energy, in which we respond that the energy requirements for production iron are high, but we have a very powerful reactor. Now, this is a slide. I didn't make the slide. One of my teammates did. I won't really write all of this. I made it much more clear. The excavation is from the drilling rover. It's really simple. The processing is from the production line. We mentioned it multiple times in our presentation. Obviously, this is a corrupt line. I maybe write it in Arabic and it was mistranslated. I'm sorry. But this is for the energy consumption that you asked for. And they mentioned that our reactor have 1.5. Here you had a lot of critique for the power, that the power allocation for life support system wasn't presented. Our reactor affords 1.5 megawatts of electricity. That's 1,500 kilowatts of electricity, which is not just the most of anyone in the competition, it's also more than what we need. We made it clear that our peak operation, it remains under the total limit, under the limitation, and we have 34% preserved electricity from the reactor, which means that we don't have to run it at full electrical power. And whenever we want, we have 34%, which is nearly half of what we're going to use. That's just allocated in case we had an emergency. Also, the power rover, we did mention with visualization that it did include a 10 kilowatt backup click power system for other energy. In case the main reactor got injured somehow, 10 kilowatts are enough for the life support system. And all of this is documented by the tables we explained and the notes. Now, for the energy consumption, that we didn't have a specific consumption level or table, and we did have a specific table, but we want to make it clear. Component level electrical demand for every individual sensor, individual light unit, individual electrical device was not modeled because such values require assumptions and work outside of our team capabilities. We can't just go like we're going to have that number of this sensor, this exact numbers, this exact model of the sensor, that this exact value is going to work, because we have a very ambitious project, as some of you critiqued, and we don't really think that such thing would actually be a requirement for the competition. And we did include a specific power table with a pie chart visualization shown at the screen. And with the note we did specify that our peak baseline and water supplement all only max out at 65.4% of our reactor capability. So we have a lot of electricity, don't worry about that. Now, for my teammate Fatima, it's your turn.
Hello, I'm Fatma Saadi from DixLab 1. At first, we explained all mission tests in the presentation and the technical file water and the oxygen system and included together with their mutation sequences. Next slide. They say no mass location was provided, but we added mass budget table was included, supported by E-chart showing the dissipation of the total system mass. Next slide. Solo expression. At no point in the presentation or technical file we solo expression ever mentioned. Next slide. Launch windows. This is file description. We address it by sending cargo on longer transfer target and the crew on a shorter one. Next slide. Next slide. Sorry. Our landing site located in Deo Heights. We found no scientific reference, identity, rock fills, or certificate cards at the selected location. Thank you for listening.
Again, we would like to make it obvious, and we would like to mention it again for the judging panel. We hope you forgive us for such a small mistake that slipped from our hands, that we had our photos and this small section. We're very sorry for that. And the voice that we're hearing right now is officially AI generated, as not generated, but artificially modified by the Zoom meeting app for clearance, more obvious voice, no other voices from the surrounding area being implemented in the mic. So yes, we didn't really think that this was AI generated or prohibited, and we're very sorry for that. We're done with our defense. If anyone else wanna say if it's their part or anything.
Thank you so much. And all of that will be taken under consideration. I appreciate you explaining that. Dex Lab 2, are you here?
Yeah, we are here.
Okay, you'll be starting in 7 minutes.
Okay.
Go ahead.
Okay, the only thing that they say that we used AI images, and I'm here to say that we didn't use AI images, and we were working to find trustable websites to find the real photos, a real sounds, a real from everything. So we really make sure to not use AI in our research, in our images, or in our presentation, because AI just will make us weaker. It will not help us at all. So we didn't use AI images, and if so, please retell me, and we're going to make sure about our research and about our presentation. We already edit our research and we improve it, so we really make sure that everything is human used, not AI. So we make sure that everything is human used, not AI, and we are making sure not to use AI at all. The last thing that I want to say that we didn't use AI in our research, so even if there's a photo created with AI, this was just to clarify our ideas and to express ourselves clearer, but this doesn't mean that we use AI in our researches. That's it. I don't guess there's anything that I'm gonna talk about more.
Do you have anything else?
No, I guess I speak everything because the only notes was about using AI images. So I just want to say that we didn't use AI images at all.
Is anyone else from your team going to speak?
No, just me.
Okay, thank you. We will start Dex Lab 3 in 15 minutes.
Okay, thanks.
Dex Lab 3 counter critique. Okay, the first team who critiqued us, it was Jonah. And they say that we propose a massive surplus in nuclear energy generation and questioned the mass to power efficiency of our nuclear fission reactor compared to a hybrid solar nuclear model. And we intentionally selected a fully nuclear energy system instead of a hybrid one because it provides the best mass to power efficiency. And because solar power in Mars is unreliable because solar air density Mars is only about 43% of the on Earth, and they operate about 10 hours per sol only and some at night. In addition, during dust storms, which are common on Mars, solar panels receive scattered sunlight that is only about 30 to 40% of direct sunlight in a clear Martian day. And solar arrays present structural complexity because they have multiple moving parts that are not practical against the adherent electrostatic Martian dust. Due to all these reasons, instead of a hybrid system, we chose the 100 kilowatt electric supercritical carbon dioxide cooled Mars surface fission reactor, because it utilizes the carbon dioxide, which is abundant in the Martian atmosphere, because it represents approximately about 95% of the atmosphere. In addition, it has a less complex structure than solar arrays, and it provides 100 kilowatts electric power all day, regardless of the weather conditions. Now for the team index, say the mission seems like a permanent colony than an initial 18-month mission. Our mission is intentionally ambitious because it is not limited to just an 18-month landing. It is designed to evaluate whether long-term human settlement on Mars is actually feasible. Therefore, the activity the crew performs includes most of the vital processes on Earth, such as agriculture, exercise, oxygen production, and water extraction. The major objective is to search for evidence of the existence of past or present life while studying the geology and climate to determine whether it could support future human settlement. However, it is not a permanent colony, though. It is intended to validate the system needed for future colonization, but the crew remained on a planned 18-month mission with comprehensive contingency procedures and capability to return to Earth if required, because at the end, astronaut safety remains our highest priority. Next slide. Will you please return to the previous slide? The previous slide, please. Okay. They claim that there are too many critical systems that can work at the same time. And we actually addressed this concern through a detailed mission timeline that schedules every major operations instead of running all the systems simultaneously in our reports. It coordinates habitat construction, oxygen production, water extraction, and agriculture, and the rest of the vital processes. It also ensures resources are allocated efficiently while considering power consumption. Okay, for the same team, they say our human operations need more detail about EVA safety, medical emergencies, exercise, conflict management, and crew redundancy. And we address this by documenting all the standards and procedures related to astronauts' operations in the report, which includes safety protocols for activities outside the spacecraft, medical emergencies, and the provision of necessary medications and conflict management. They also claim that oxygen and water systems need clear calculations, storage plans, and backup systems. And all these points were addressed in our file, but they weren't mentioned clearly in the presentation to do the short presentation time. Okay, the last claim is our construction plan is overly optimistic, particularly using 252 tons of marsh and regolith and completing construction within 4 to 6 weeks. But these values were not estimated randomly. They are based on detailed calculations documented in our report. Because our power distribution analysis showed that 3 nuclear reactors with a combined electrical output of 300 kilowatts can supply the 50,000 kilowatts required for construction in approximately 167 hours of actual machine operating time, or about 7 days of continuous operation. But we intentionally extended the construction period to 4 to 6 weeks as a conservative estimate to allow enough time for equipment setup, material handling, maintenance, and other delays that may have happened. And this timeline is appropriate because the reactors provide continuous power, allowing the 3D printers, drilling equipment, mixing machines to operate whenever needed without interruptions from the Martian day-night cycle or dust storms. After construction, the colony requires only about 45 kilowatts of electrical power, leaving an energy surplus that can be stored as a reserve. Therefore, the proposed construction timeline is practical and fully supported by our calculations, which are mentioned in the report. Okay, this was Team Dex Lab 3. Thanks for listening to us.
Thank you so very much. Great presentation. Go right ahead.
Right, so we're Team Red Frontier, and here are rebuttals.
Before we begin, we'd like to thank Mars Society and all of the teams for the thoughtful questions and constructive feedback you gave us during the design review. One of the biggest lessons we've taken away from this competition is that designing a human mission to Mars is never about finding one perfect solution. It's about understanding the engineering trade-offs behind every decision. Many of the teams raised similar questions, so rather than answering each team individually, we've grouped our responses into key areas of science, engineering, and human operations. Our goal today isn't simply to defend our design, it is to clarify the reasoning behind Alethea, explain evidence that supports our decisions, and acknowledge where your feedback has helped us communicate our design more clearly. So with that, we'll begin with science.
So we had several teams questioning the reasoning behind the selection of Oxyaplanum as our landing site. Although all teams that critiqued us accepted that the value Oxyaplanum brings, they had said that science seems to take precedence over crew safety and asked that if the ESA chose it as a site for their rover mission and not a manned mission, then why go there? So first of all, Alethea is primarily an astrobiology mission. It is not. Its principal objective is finding past life on Mars and not for long-term human settlement. With that objective, we collectively brainstormed and shortlisted a few locations that could have potentially harbored life on Mars, such as Marth Vallis. Oxyaplanum was chosen because the ESA evaluated landing safety, terrain safety, elevation, and landing hazards. Just because they are not doing a human mission to Oxyaplanum, it does not mean Oxyaplanum is not a right candidate for human exploration. Cargo-first architecture will make sure all the surface systems are validated, radiation hazards are weighed in, and terrain mapping is done for crew landing. And only then a collective decision will be made for when the crew will depart from Earth. So secondly, we agree that ancient water doesn't mean accessible water. However, we had never stated that was the reason we selected Oxyaplanum. Its ancient aqueous environment and Noachian clay deposits make it one of the best locations on Mars for preserving potential biosignatures. Our mission focuses on astrobiology. If accessible water is identified, only small quantities would be used for scientific investigation and ISRU demonstrations, not as the primary water source for crew survival. Secondly, our algae bioreactor, many teams questioned its reliability as a source of oxygen. We'd like to clarify that the bioreactor is an experimental sustainability system, not our primary life support system. Our primary oxygen supply comes from water electrolysis supported by water recycling and emergency oxygen reserves. Therefore, if the algae culture failed, mission-critical life support would continue operating without interruption. So why exactly do we have an algae bioreactor in the first place? Well, in recent years, biotechnology has become increasingly important for space exploration. Algae has been investigated for oxygen production, carbon dioxide removal, biomass generation, and even future life support systems. The biomass produced can also provide a nutritional supplement. In fact, spirulina, a type of blue-green algae, is already widely consumed on Earth because it is rich in protein, vitamins, irons, and other essential nutrients. Alathea isn't relying on algae to keep the crew alive. We are just evaluating the extent to which it can become a reliable supplementary life support technology for future long-duration Mars missions. Engineering.
Okay. The engineering questions we received were very thoughtful and challenged us to think more carefully about how we communicated our architecture. We'd like to take this opportunity to clarify some of those design decisions. Firstly, a team claimed that DSOC cannot be used for rovers and drones because dust interrupts laser communication. Our rebuttal for that would be that we are not proposing DSOC for communication between rovers, drones, and the habitat. Our architecture uses a local wireless network for surface assets, while NASA's Deep Space Optical Communications concept is used for long-distance communication between Mars infrastructure, relay orbiters, and the Earth. Communication between habitat and rovers is achieved through a local Wi-Fi mesh network. Communication between the habitat and the Mars orbiter is via a high-gain optical link. Communication between the Mars orbiter and Earth is the one which uses a DSOC/Deep Space Network as per NASA's architecture. Okay. Next, this is one of the strongest critique we've received. A team thought that we stated, redundant architecture improves reliability and reduces communication latency. This phrase may have unintentionally suggested something different from our intended meaning. It's a fair point, and we are not challenging physics. No communication architecture can reduce Earth-Mars transmission delay because latency is fundamentally limited by the speed of light. Depending on planetary positions, that delay is about 4 to 24 minutes one way. Our point was that a hierarchical local network improves operational efficiency and responsiveness between surface assets while redundancy increases reliability by providing alternative communication paths if one system fails. Okay. Next, this is one of the strongest critiques that we've received. Oh shit, my fault. Okay. On the autonomous habitat placement, an autonomous cargo deployment is a key feature of NASA's Mars architecture strategy. Surface infrastructure is deployed and authorized before crew arrival to reduce operational risk. Our mission follows that same phased approach, where autonomous systems establish and verify critical infrastructure before astronauts depart from Earth. Okay. So, system redundancy. A team asked why we would use 3 surface systems, and this was an intentional engineering trade-off. Rather than relying on a single rover for every task, we distributed capabilities across specialized platforms with specific instruments on each of them, and not duplicating capabilities. The Frontier rover conducts autonomous science before the crew arrives, and the drone provides aerial reconnaissance and hazard assessment. Okay.
The next couple of critiques that our team received was on the suit, so we wanted to make some clarifications. The team's critiques are on the slide in orange. The first critique that we got was on the reliability of our Orion suit as an IVA suit and its non-compatibility with the Martian surface. In the critique, the team quotes that we said in a depressurized cabin, which is exactly what we meant. According to NASA and many other sources, a depressurized cabin is when there is a loss of controlled air pressure within a spacecraft or habitat. Our specific wording, depressurized cabin, makes it clear that we meant inside a spacecraft, not outside on the Martian surface, where any other existing IVA suits would not be able to withstand any conditions. The second critique that we got on our suits was that the NASA Orion IVA suit lacked radiation protection. To clarify, the purpose of an IVA suit is to protect astronauts inside a spacecraft during phases of flight, like the launch, docking, and re-entry processes. IVA suits rely on the spacecraft's integrity for radiation protection. Additionally, there are currently no IVA suits existing that protect astronauts from radiation. We hope this clears up a few misunderstandings on our IVA suit.
If someone is speaking, we cannot hear you.
Oh. Well, I can hear the video. I'm not sure why it's not. The video is not working.
I don't see a video and I don't hear anything. I just see a slide that says human operations. If this is what the video is about, if you could just read that, that would be great.
Hold on. So, you see the human operations slide, and then okay, whatever. So, so for human operations, first of all, there was the claim that there is no emergency command structure. So, as previously stated during our presentation on Monday, the leader holds an all tie-breaking authority during an emergency, and the crew is psychologically pre-committed to respecting the leader's decision. If the dispute involves the leader, authority automatically falls to the psychologist for a final decision. If both Marsonauts are incapacitated, then the trauma surgeon takes authority to ensure functional redundancy. Secondly, sleep patterns not right per SOL, claiming we were wrong by saying astronauts will get more time on Mars. A Martian SOL is 24 hours and 39 minutes, and our scheduling protocol utilizes this for rest and circadian adaptation. So astronauts do get more time on Mars. Thirdly, the claim that there cannot be equal hours for field and lab astronauts. This critique lacks the specificity required for a definitive response. And finally, strict schedules will cause distress, and the example they used was when American astronauts canceled communication with Earth on Skylab 4. Now, the incident referred to in this situation is an example of crew rebellion caused by micromanagement from Earth. Our operational model operates and prevents this by using macro objectives. Mission control sets macro objectives, but the Mars crew maintains full tactical autonomy over how and when the daily tasks to achieve the milestone will be done. So, thank you. To conclude, we'd like to thank everyone once again for the thoughtful questions and constructive feedback. The review process gave us the opportunity to reflect on our design and, more importantly, how we communicated it. We hope today's clarifications have demonstrated that Alethea is built around evidence-based engineering, meaningful deployment, redundancy, and careful systems integration. Like Carl Sagan said, we are a way for the cosmos to know itself. Through Alethea, we hope to take one more step in that journey and may discover the evidence that helps answer one of humanity's oldest questions: has life ever existed beyond Earth? Thank you. That's it.
Thank you so much for your presentation. The next presentation is Project Etheria. Are you present?
Yes, we are present.
Okay. You will begin in 8 minutes, so about 7.5 minutes. So get everything ready and we will return then.
Okay, thank you.
Go right ahead.
All right. Good morning, esteemed judges, members of the Mars Society, and fellow competitors. We would like to begin by thanking the reviewing teams for raising these concerns. Criticism is essential in engineering because it gives a team the opportunity to clarify its decisions, present further evidence, and correct misunderstandings. Today, we will address 4 areas shown on this slide. First, we will clarify the AI allegations. Second, we will answer Sojourners 92's questions about solar degradation and emergency power. Third, we will respond to Dowhi's claims regarding crew selection and radiation protection. Finally, we will address Red Initiative's concerns about habitat size, reactor mass, mission balance, and scheduling. Our submitted report was approximately 25 pages long, while our original presentation was limited to only 20 minutes. It was impossible to display every calculation, study, procedure, and design justification on the slides. That does not mean those details were absent from our mission. We will now clarify them directly.
Okay, this slide shows the actual development of the astronaut artwork through 4 visible stages. Version 1 established the original outline and composition. Version 2 added flat colors. Version 3 added the Martian background, lighting, and environmental details. Just to clarify, this is the artwork development and our miscaption on the Firefly. Version 4 applied a texture pack and a final visual polish to an image that already had been designed. Adding texture packs could possibly show traces of AI due to lots of detail, whereas every version before does not, and this information is from a trusted source, which is Lovart. The important evidence is the progression. The final artwork did not suddenly appear. Its astronaut positioning, horizon, and composition was followed from the original outline to the completed image. This image was mistakenly captioned as being associated with Adobe Firefly due to a misinterpretation of a tool label. We thank the reviewers for pointing this out because it allowed us to identify and clarify this miscaption. We would actually caption this final texture in visual polish applied in Adobe Illustrator using a grain/noise overlay. Conventional enhancement of an existing image, such as adding texture, grain, lighting, or contrast, is not the same as generating the complete artwork using AI. The underlying design already existed before the final enhancement stage. We'd also never intentionally mention an AI program directly in our own submission while attempting to conceal its use. That would make no logical sense. Its open appearance was the result of an inaccurate software caption, not in an attempt to disclose one thing while hiding the other. As well as to add, my parents are in interior design field, and I've been taught to use these digital art tools since a young age, and these tools do not have the use of AI. The evidence displayed here shows a real progressive creation process, and we accept that the caption should have been checked more carefully, but that mistake does not erase the visible development of the artwork or affect any technical part of Project Etheria, because you should note that this image has no relevance to any component in our project.
This slide shows our academic integrity through the original technical concepts created for Project Etheria. We used Blender and CAD to produce Arcadia Shield Habitat, Greenhouse, Prospect Rover, Argo Rover, and the Falcon drone. Each model represents a system that is described in our report and connected to a specific mission function. The Arcadia landing site figures also come from real mapping and orbital data. These visuals show real project work and original mission concepts.
Presentation design. We also designed and assembled the presentation ourselves. We selected the information, organized the slides, positioned the text and images, established the visual hierarchy, and condensed our report into the final presentation. The detector results shown here identify the slides as real. This is because they contain CAD renders, diagrams, resized images, backgrounds, text formatting, and visual adjustments. A detector looking at the final exported slide cannot determine who designed the rover, developed the habitat, or calculated the power system. It only analyzes visual characteristics in the finished image. And this slide, therefore, shows that digital presentation design, which is basically a template, is not proof that the work inside it was generated by AI. Every single word here is from our report.
The strongest evidence behind our project is the full written report. We tested the 3 central divisions of Project Etheria with the verified NSS AI detectors, which is copy leaks. Human operations returns 0% AI content, science also returns 0% AI content, and engineering also returns 0% AI content. These are not 3 small paragraphs. They represent essentially the complete technical substance of Project Etheria. Our scientific studies, engineering systems, crew operations, calculations, procedures, and emergency planning. We understand that no detector, whether its results support or challenge us, is perfect. However, if detector results are being considered as evidence, then these 0% results must be considered fairly. More importantly, we understand and can defend what we wrote. We can explain how the system works and what we selected and why we selected them and how they connect. Our report was researched, written, and developed as one complete mission proposal.
Time log. This slide displays our development log, which records approximately 105 hours of work. The spreadsheet was created on May 23rd, when we had already contacted Ms. Willett early so that we could begin organizing the project properly due to exam conflicts. The log separates our work into specific tasks, including research, writing, calculations, citations, formatting, and modeling. It records our work on solar power, batteries, storm operations, water extractions, and many more. We recently reviewed the spreadsheet again because we had a lot of missing descriptions, so we added tasks that were finished later and ensured the final log accurately represented everyone's contributions. So this demonstrates that Project Etheria was developed through an extended, divided, and traceable work process.
As a brief example of why detector results require context, the same system classified the Mona Lisa as highly likely to be fake and assigned The Starry Night by Vincent van Gogh a substantial AI likelihood, even though obviously AI didn't exist 300 years ago. If the astronaut illustration remains a concern after this explanation, we respectfully ask that our report be assessed without it. The image has no effect on our research, calculations, mission architecture, or engineering conclusions. Our countless hours of hard work should not be put down due to a misinterpretation of a single irrelevant image.
Okay, now let's talk about the regular critiques. So Sojourner 92 asks what minimum power threshold would preserve critical life support during a prolonged dust storm, and which scientific systems would be powered down first. So this is a really good question, and it was actually already answered within our full report. So Project Etheria does not depend on solar power as its primary survival source. Our 40 kilowatt class fission system supplies continuous base power, while solar panels provide supplementary energies and additional redundancy. NASA likewise describes fission surface power as capable of providing continuous electricity regardless of environmental conditions on the Moon or Mars. Our normal operating demand is approximately 30 to 35 kilowatts. During a serious dust storm, the base would enter an emergency storm power mode, maintaining approximately 20 to 25 kilowatts for critical systems. These protected loads would also include atmospheric circulation, oxygen generation, carbon dioxide removal, thermal regulation, water recycling, medical equipment, and command computers, as well as essential communications, optional laboratory instruments, non-essential external observations, and manufacturing would be reduced first. Rover charging would be delayed, and greenhouse lighting could be reduced to crop survival levels if it's necessary. The critique assumes that losing solar production would leave our mission without a defined survival plan. That is incorrect. Solar is supplementary, while fission power, or FSP, protects the critical load. This is also an example of detail that cannot all be spoken during our 20-minute presentation, but was included in our power distribution and emergency mode sections.
Okay, now for Dao Hai. Dao Hai first argued that our crew selection approach would result in choosing less qualified women over more qualified men. That claim misrepresents our selection system and relies on the unfair assumption that female candidates would be less qualified. Project Etheria uses merit-based selection. Every crew member must satisfy the mission's technical, medical, psychological, and operational requirements. Candidates are selected according to their expertise, teamwork, physical suitability, mission role, and ability to operate during long-duration isolations. NASA's selection process similarly evaluates candidates' qualification and advances the most highly qualified applicants. Its published professional, educational, and medical standards are not lowered according to gender. Our inclusion of women does not replace merit. Women can meet the same standards and perform these roles equally well, and if not better. and depending on the individual and required specialization, may be the strongest candidate available. Being a woman and being highly qualified are not contradictory. The second criticism states that an inflatable habitat does not provide sufficient radiation protection. That would be correct if we relied exclusively on a thin inflatable wall, which we do not. Our habitat uses a multi-layer expandable pressure structure based on transhub concepts. NASA's inflatable pressure vessel research similarly describes a pressure bladder restrained by high-strength structural fabric. Our deployment after our habitat is covered with approximately 2.5 meters of Martian regolith. That material provides the main external radiation barrier. The habitat also includes a protected central storm shelter surrounded by water, food equipment, and other hydrogen-rich materials. The crew additionally uses radiation monitoring, personal dosimeters, forecasts, and EVA exposure limits. Therefore, the critique evaluates the inflatable shell alone while ignoring the regolith, internal shielding, shelter, and operational protections that form our complete system.
Okay, now let's look at the critiques from Red Initiative. So Red Initiative claims that our 500 square meter habitat is unnecessarily large and recommends beginning with a smaller structure that can expand later. That recommendation, as you can see, is already in our report and design. The 500 square meter value represents the approximate maximum area of the completed expanded habitat. It does not represent one enormous structure deployed immediately for the first crew. Our initial core is approximately 150 square meters. Additional connected modules expand the base as its population and operational requirements increase. The modules are inflatable and can therefore be transported in a compact form before being expanded on Mars. NASA states that expandable habitats require less payload volume during transportation and can provide significantly more usable area after deployment. NASA's TransHab concept was itself designed as a multi-level inflatable living environment, while Beam has demonstrated expandable habitat technology aboard the International Space Station. Our floor area is also functional. It accommodates crew quarters, command operations, laboratories, medical isolation, exercise, hygiene, storage, life support equipment, and essential shelter. A crew living on Mars for an extended period requires room to exercise, conduct science, repair equipment, and separate work areas from sleeping areas. Therefore, the critique's proposed solution, begin smaller and expand, is not an alternative to Project Etheria. It is actually exactly how the Arcadia Shield habitat operates.
Okay, so another claim by Red Initiative is that NASA estimates a 40 kilowatt reactor to weigh approximately 6,000 kilograms and therefore concludes that our 2,400 kilogram value is incorrect. That is not what the NASA source states. NASA describes 6,000 kilograms as a mass target for its complete 40 kilowatt lunar fission surface power demonstration. NASA also states publicly that the proposed system should remain under 6 metric tons. A target or maximum design requirement is not a measured universal mass that every 40 kilowatt reactor must have. The NASA figure also applies to a complete deployed power system. That architecture can include the reactor, power conversion, heat rejection, shielding, cabling, control systems, and deployment equipment. Project Etheria's 2,400 kilogram value represents our projected Mars-specific reactor and closed Brayton power conversion installation. It is not intended to be a direct copy of NASA's lunar demonstration package. At 2,400 kilograms and 40 kilowatts, our estimated is 60 kilograms per kilowatt. This is an advanced estimate for a future Mars mission based on improvements in Brayton conversion, thermal management, and system integration. Technology adaptations would be required, but that does not make the figure physically invalid. Red Initiative is free to question our design margin or recommend additional contingency. However, it is wrong to claim that NASA's 6,000 kilogram maximum target proves that our system must weigh 6,000 kilograms as well.
Now let's move on to the next critique. Red Initiative claims that Project Etheria focuses too heavily on engineering and gives too little attention to science or crew operations. That criticism overlooks the full scope of our mission. Like we stated earlier, we had limited presentation time, but our report contains an entire science section built around determining whether Arcadia Planitia is suitable for long-term human settlement. First, we investigate subsurface ice and water resources by using Prospect to locate, characterize, and sample buried ice. This is not simply about confirming that ice exists. We study its depth, purity, accessibility, and usefulness for drinking water, oxygen production, and future fuel generation. Second, we study sustainable food production and bioregenerative systems through greenhouse crop trials. We examine plant growth, water recycling, nutrient use, and how food production can reduce dependence on Earth. Third, we investigate radiation exposure and shielding effectiveness by monitoring radiation inside and outside the habitat by evaluating how well regolith, water, and habitat materials protect the crew. Fourth, we study Martian climate and dust. Our dust research is not just repeating the known fact that dust causes degradation. In fact, we measure how dust affects an integrated Mars base over 18 months, including solar array output, radiators, rover visibility, drone performance, filters, and airlock seals. We then produce maintenance schedules, cleaning requirements, and material recommendations for future crews. We also conduct long-term observations of the Martian moons known as Phobos and Deimos, multispectral, thermal, and high-resolution cameras to study surface features, orbital behavior, and possible resource potential. Crew operations are also clearly addressed. Each Marsonaut has defined roles, structured work periods, exercise, meals, scientific tasks, maintenance, communication, recreation, and rest. Daily health and psychological check-ins support crew well-being, while conflicts are handled through a clear decision hierarchy led by the commander and a relevant specialist. Engineering received detail because none of this science can happen unless the crew has power, water, oxygen, and radiation protection. Science and engineering are not competing priorities in Etheria, they're designed to work together.
Lastly, Red Initiative claims that our schedule wastes time because major crop and water experiments do not immediately begin at maximum scale. Full operations are not declared until Sol 261, and the final phase prepares for the following mission. That criticism is based on a false interpretation of our timeline. The crew is actively working from the moment it lands. During the activation phase, the crew inspects the habitat, verifies pressure and integrity, starts and calibrates life support systems, confirms communication, and checks whether transportation or landing damage any equipment. The crew then prepares the rovers, maps safe routes, monitors radiation, surveys the landing area, and confirms subsurface ice and tests water extraction equipment. Those activities are not wasted preparation. They are essential operations and produce scientific and engineering data. The water system cannot safely become a major life support input before the crew confirms the ice deposits, characterizes possible contaminants, measures extraction rates, and validates purification. Similarly, crop trials cannot responsibly begin at full scale before the greenhouse has stable temperature, humidity, lighting, nutrient delivery, carbon dioxide control, and clean water. NASA describes habitation system development as a complete process involving research, design, prototyping, testing, verification, and operational support. Testing and verification are therefore essential parts of preparing a human-rated system, not evidence of inactivity. The term full operation means that all major systems have been validated and can function together at their intended long-term capacity. It does not mean that no science occurs before Sol 261. The final phase is also misrepresented. The crew does not spend more than 200 sols doing nothing except waiting for another mission. They continue experiments, maintenance, environmental monitoring, and exploration, while also constructing infrastructure, documenting lessons, and preparing the colony seeding cache. Project Etheria was specifically designed to support future missions. Preparing equipment and infrastructure for the next crew is therefore one of the mission's objectives, not wasted time. The detailed timeline could be explained line by line during our original 20-minute presentation, but it is clearly documented in our report. The critique confuses cautious system commissioning with inactivity and long-term settlement preparation with wasted effort.
Okay, to conclude, we sincerely thank every team that reviewed Project Etheria. You have shown the progressive development of the astronaut image, clarified the miscaption, presented our original CAD and Blender models, demonstrated our written reports detector results, and shown our recorded development process, which displays all of our academic integrity. We have also demonstrated that several technical criticisms do not accurately represent our mission. Our fission system preserves critical power during dust storms. Our crew is selected according to merit, and including qualified women does not weaken that standard. Our habitat our habitat begins with a smaller inflatable core and expands toward the full configuration. Our radiation protection depends on regolith, internal shielding, a storm shelter, and operational controls, not just an inflatable wall. NASA's 6,000 kilogram figure is a system mass target, not a universal minimum reactor mass. And our report includes dedicated science, engineering, human operations, timeline, and risk sections. Finally, our stage schedule contains active testing, research, and preparation from the beginning. Project Etheria is an ambitious conceptual mission, but its decisions are connected, researched, and defensible. Thank you.
Thank you so much.
Thank you for your very comprehensive presentation. The next team is Sojourner 92. Are you available?
Yes, we're here.
Okay, are you ready to begin?
Yeah, I can start now.
Okay, go right ahead.
Okay. Hello, everyone. I'm here today to respond to the main critiques against our team, Sojourner 92, and clarify many of the criticisms that previous teams have raised against us.
Will you be sharing a presentation or screen?
No, we could not
Okay.
prepare our presentation in time,
Okay, go ahead.
So, as we went through the video from Wednesday, we found that many of the critiques were actually based on misunderstandings. So we wanted to use this as a session to clarify what our mission actually proposes. Our mission is not lava tube dependent. It is not to set up a colony in a lava tube. It is a surface-based, risk-reduced human mission designed to answer one question: whether Martian lava tubes can serve as safe, long-term habitats for future crews. The crew's survival during this mission depends on a surface base, not on moving underground. So one criticism was that our project focused way too much on science and not enough on engineering. In the full report, engineering is actually the strongest part of the design. We include a landing site study, habitat architecture, radiation protection strategy, water and food systems, life support, power systems, vehicles, and a full mass budget. The presentation could not show all of that detail, but our report does. Our mission is intentionally structured in 2 launches and 2 phases. Launch 1 delivers cargo and infrastructure, and this allows the infrastructure to be set up before any crew arrives, and that's what Launch 2 does. It delivers the 6-person crew with their food and water and any other instruments or equipment needed for survival on Mars. And then we've divided our mission into 2 phases. Phase 1 establishes and verifies and tests the surface habitat. And phase 2 is where most of the exploration is done. It performs lava tube reconnaissance, astrobiology experiments, and evaluates how the mission is carried out. Another critique was that our habitat design was unclear. To clarify, our habitat is made up of 2 connected modules. One is a small rigid habitat for crew quarters, life support, medical bay, storage. And the second habitat, or the second module of our habitat, is an inflatable module for scientific experiments, agriculture, and just a communal space. This was important to highlight because some critiques assumed that we were depending on lava tubes for protection right away. We are not. The rigid habitat is actually our primary living space from the beginning of the mission. We also specifically placed sleeping quarters in there to reduce cumulative radiation exposure when the crew is resting. Another major concern raised was that lava tubes are risky. They're unstable. We completely agree. That is exactly why our mission does not assume immediate human occupation of lava tubes. Instead, our surface habitat uses a hydrogen composite shell plus regolith shielding to protect the crew from radiation. And the lava tube is actually treated as a reconnaissance target, not as a required habitat. We use drone mapping, LiDAR, and imaging and environmental sensing to first develop a map of the cave and record if there are any instability or risks for future habitation. And then only does the crew descend into the lava tube, only if the site appears safe. Some teams also criticize our plan as inefficient because we establish a surface base and only later investigate lava tubes, but this is actually risk reduction. The first human mission to Mars should not depend on an unverified underground environment. The surface habitat gives the crew a known operational base, stable life support, a medical area, communications, power, greenhouse capability, and a safe place to return to after every exploration. So the surface base is not wasted mass, wasted time, or wasted effort. It's actually the mission's backbone. Another criticism was that our landing site may be too far from the lava tube, or that it prioritizes the wrong things. We chose Pevanus Mons because it offers better characterized and more structurally promising skylights than other nearby volcanoes like Arcia Mons. Our base is placed about 10 to 15 kilometers from the primary skylight so that it's close enough for repeated reconnaissance, but also on terrain that didn't collapse because of faults in the Earth or in Mars. So this is really a trade-off between safe landing conditions and stable terrain and operational mobility. We also support this with a pressurized rover for astronauts to conduct longer traverses, so they can spend up to 3 days in that rover. That detail is found in our report. Some critics actually said our crew was too specialized and not cross-trained enough. In our human factors section in our report, we actually say the opposite. Each crew member actually had a primary specialty, which is what was highlighted during the presentation. But every function is supported by cross-training and role redundancy. We selected our crew not just for the technical expertise they have, but also the ability to adapt when something goes wrong or an emergency occurs. Our design states that mission continuity must remain possible, even if one person becomes unavailable. And that includes habitat maintenance, emergency response, rover operations, scientific sampling, and medical care. So the mission does not rely on one person being the sole holder of any function. Another criticism was that our crop plan was unrealistic, especially regarding regolith and food dependence. And we would like to point out that our greenhouse is supplemental. It's meant to be a supplemental source, not the primary. The majority of mission food is still transported from Earth. The greenhouse mainly improves nutrition, freshness of the food, and acts as a boost for crew morale. We do not assume immediate use of untreated Martian regolith. During the first part of the mission, crops are grown hydroponically. Regolith use is only considered later after we have bioremediated the regolith, specifically because perchlorates are toxic for organic compounds. We recognize that. That's our bioremediated regolith is our plant. So our agricultural plan is not based on the idea that astronauts simply plant plants directly into untreated Martian soil and survive on that. Some teams said our water or oxygen systems were also unclear, and we wanted to clarify that. For water, we do not rely on Martian water extraction intentionally for this mission because the technology used to purify, extract, and drink that water is too immature. Instead, we use transported water from Earth and a water recovery system like the one on the ISS with over 90% recovery rate for water. That gives us a more reliable and more mature and more proven water architecture. And for oxygen, similar to the ISS, we use an oxygen generation system based on electrolysis electrolysis using recycled water. So our life support design is based on ISS-derived systems that are already technologically proven and technologically mature, rather than optimistic scaling assumptions. Another repeated criticism from multiple teams that we saw was that solar power is risky on Mars. And we do agree that solar power alone is risky. That is why our design incorporates a secondary power source. So our solar arrays are our primary power, but we also have a regenerative fuel cell for storage and an MMRTG for emergency backup power. Now, I'd like to note that the MMRTG source is not intended to run all mission operations indefinitely. It's just there to preserve what's necessary for survival during periods of reduced generation, such as dust storms. So our power architecture is not a single point of failure. Some critiques said we did not provide enough payload detail, but in our report, we actually include a mass budget totaling about 28,000 kilograms, leaving roughly 2,000 kilograms or about a 7% margin, which is within the 30-ton constraint. That budget includes habitat systems, life support systems, food, water, rovers, suits for EVA, greenhouse hardware, and the power systems. So we do have a quantified mass plan. It just wasn't shared in the presentation due to the time constraints. And lastly, one of the more valid critiques raised, in our opinion, was the question of the 70-day gap between launch 1 and launch 2. That is a valid point. And if challenged on this, I am acknowledging that interplanetary launch windows impose constraints that may require refinement of the exact timing assumption. The purpose of that interval, though, was to allow cargo systems, especially the regolith excavation system, to prepare the amount of regolith required for our habitat to begin before crew arrival. So if needed, we would revise that timing to align more explicitly with more realistic launch window constraints while still preserving the same core mission logic of cargo first and then crew second. Finally, there was also a concern that our team actually used that our team sourced our images from AI, but we wanted to clearly state that we did not use AI because at least even for our images, the whole presentation was text-based. There was no images on there. So we just wanted to clarify that. If any confusion came up, it might have been because our science section mentions that we use AI as part of the mission, something that the astronauts would use as an in-mission tool for one of our experiments. That is actually part of our proposed mission science payload. It's not a writing or presentation tool that was used to create our report. We are happy to clarify our sources, research process, and document history if needed. So to conclude, Sojourner 92 is a surface-based Mars mission with a clear engineering background. It contains a shielded surface habitat, mature life support systems, a hybrid power architecture, rover-supported exploration, a quantified mass budget, crew redundancy, and cross-training, as well as a deliberate approach to lava tube reconnaissance. Our mission does not assume that lava tubes are immediately habitable. It is designed to test that question safely while keeping the crew protected in a fully functional surface base throughout the mission. Thank you. I'd also like to thank all of the teams here for reviewing our design and providing these critiques. They helped us understand our mission better as we were developing our rebuttals. Thank you.
Thank you so much for your defense. And the next team up is Eric, Isaac, and Calvin. Are you guys ready? You start in 5 minutes. Go right ahead.
Right. So this is the Dalhai Mission to Mars team, and we will respond to the critiques that we got on Wednesday. One of the biggest critiques we received was the lack of, what was it? There's a lack of crew redundancy, as the majority assumed that there was only one engineer who knew how to handle the engineer tasks, one medic who knew how to handle the medic tasks, and one paleontologist. However, this is not true. I believe, due to a huge misunderstanding, most people assumed that one engineer was the only one who had skills in engineering. But due to our diverse training, and as one of the teams said, cross training, all of the crew should be able to handle the tasks at a basic level. The job of an engineer is to handle complex engineering, but all of the crew should be able to handle simple engineering. So while we only have one engineer, the other crew members should be able to handle those tasks if something goes wrong. And also, the reason we chose 3 people for the crew was that an odd number worked best for solving arguments, as that can lead to a vote. Because otherwise, if you have an even number of crew members, that can lead to a tie, and that creates complications. And having 5 people when you only need 3 is illogical, due to the fact you're just wasting more resources on keeping them alive, such as food, water, when they don't necessarily need a task other than backup. That's why we went with 3. 3 was the most logical for us, if all of them were cross-trained. The other response we got was that it was illogical. People thought it was illogical that we were only sending members of NASA to Mars. But we didn't do this due to nationalism or any of that. We did it because of logistics. Currently, NASA is the organization that's leading the charge to Mars, and they have the most resources to lead an expedition to Mars. And due to the current geopolitical stance in the world, that creates complications for leading an international mission all the way to Mars. So we thought it was best to use NASA for the first mission to Mars. We don't believe the United States of America should be the only nation heading to Mars. We just believe, due to complications as of now, it is best to send NASA first, so we can create a base there for human life eventually. And the majority of our research is based on NASA sources, such as the ISS and more. So it would be logical for us to use NASA as the one that goes to Mars, as that's the organization we based our research on. All right, my partner can go now.
For the power generation, we received criticism on the ability of our power generators to continue functioning after something may happen to the engineer. However, this is able to be prevented, as the Kino power reactors are designed to work with no maintenance, and the solar panels are relatively easy to maintain for all crew members. We also received criticism on our reactors redundancy, our electrical systems redundancy, which we detailed that each reactor would be in a different crater to help prevent any malfunctions to spread across our reactors, and always ensuring that our astronauts will have power for essential life support system. On the next slide. Our life support system was also criticized, which has already have functioning prototypes and consists of a closed loop survival system, allowing us to ensure that our astronauts are always safe and will be able to function and survive. Our next criticism is on our Winky drill capabilities, which is on the next slide. And here is where we got our source, that the Winky drill can go down to 100 meters from the University of Minnesota. The rover itself was not able to go down far because that was not what it was solely designed for. It had other missions in mind, as well as having to drive around being a rover. So it had a weight limit. However, we have a much higher weight limit that we can utilize to ensure that our drills are able to give us what we need on a scientific basis as well as a geological basis. And on our next slide, it details criticism on our habit material. It was stated that our titanium outer shell was our main radiation protection, which it in fact wasn't. Our titanium shell serves as a hard shield to ensure that our astronauts will be completely protected from micrometeors or any events that may happen, as our primary mission is to ensure our astronauts are safe. Our primary way to stop radiation is lithium borohydride, which can reduce the radiation from 133.9 MSV to 49.6 MSV for 18 months, which is less than the amount on the International Space Station, which shows that our habitat is able to provide protection from the outside radiation. The method in which we install our titanium outer shell is also criticized, but we detailed that it would be constructed along with the rest of the habitat by our rovers that manned before the astronauts crew does. And on the next slide is our mass budgeting. We had two criticisms here. The first of which was that our titanium was not included in our mass budgeting. However, we included the titanium mass budgeting in each module of our habitat, as all the materials that would create the module is included within the module. So this includes all the materials we use to build our habitat. The next criticism is that our kinopower reactors are too heavy and therefore we should be disqualified, since we cited 3 weighs 1,500. However, what we are stating in our chart is that 1 kinopower reactors weigh 1,500 pounds, and 3 of them combined, and we have a 3 total. So the 3 combined would weigh 4,500, which is included in the total weight. This goes for all of our masses as well, as it would be based on each unit weight for our weight section, with the quantity multiplying to the weight section to receive our final weight result.
Finally, DexLab 1 stated that we passed the weight limit, but I am unsure if they meant another thing. But as the chart clearly shows, we did not cross the weight limit, and we are below it. And there were 2 other pieces of criticism that we received from DexLab, but I am unsure what happened, but it is illegible, and we were not able to understand what they were asking us, what they were criticizing us on. And that should be it. Thank you very much.
Thank you.
Thank you so much for your defense. Let's see, is the next team here Red Initiative?
Yes, we're here.
Okay, we'll start in 10 minutes.
See my screen now?
Yep, go ahead.
Okay, so hello everyone. My name is Miriam. I'm from the Red Initiative team, and together with my teammates Asa, Pari, and Jayan, who unfortunately couldn't be here, so it's just me, Asa, and Pari, we're going to be going over some critiques that we got on our presentation. And before we move forward, we would like to say that we're actually grateful that we're able to receive these critiques, because it just helps us think again about certain decisions that we made and really understand how complex a Mars mission can truly get. So we will be going through some of them, and hopefully we can answer some of your questions.
So first of all, we're going to start with Team Etheria, and their first critique was about the phase timing. So they mentioned that 4 weeks is too little to set up the autonomous systems and get them tested before the astronauts arrive. But really, this decision was taking into account the time constraints. So we had 1.5 years only as for the entire mission, and 4 weeks was the maximum amount of time that we could that could be allotted without having the astronauts orbit Mars while the autonomous phase is complete. So if the astronauts were to orbit Mars, I think first of all that would increase the complexity of the mission, and also it would be a waste of time because there's not much up to do there. So we really tried to go with the maximum, which would be 4 weeks. And also we would like to elaborate on this point that all these autonomous setups will be tested on Earth in artificial Martian environments to ensure no uncertainty in the ability of the robots. So obviously, in any space mission, there's a lot of risks, and we are very aware of that. But we're trying to test everything in the most efficient way possible. And also, when we were designing this mission in the engineering section, we tried to find the most straightforward way to do the hardest thing. Okay, so for us, when it came to set up the main habitat, we thought about autonomous docking, which is not very new, considering that SpaceX's Crew Dragon does it on the ISS. They autonomously dock with the ISS. So we're kind of going off of that because autonomous decision is actually quite used in space exploration. They also had a question regarding the human robot, and they basically stated that would be useless. And I think they might have said that because we didn't really quite go over what it was because of time constraints. So actually, the humanoid robot is kind of a home assistant. It never leaves the habitat at all. It always stays in the habitat. It's not meant for any expedition or any risk taking or anything like that. We employed this humanoid robot so that the crew could focus on the science more. So let's say the crew's in the habitat, okay, and maybe something goes missing, okay, maybe they're searching for a spare part, or they just like go around the habitat searching for it, or anything like that. They don't have to worry about that since the humanoid robot could take care of that. Okay, so this is really just to keep track of crew schedule and just to maintain the habitat while the crew can get to focus on the core goals of the mission. And they also mentioned the medical crew confusion, and honestly, there's not much to say here because this was just a typo. The nutritional psychologist is also a trauma surgeon, but this was just a typo, so there's not much to say here. And then finally, there was questions regarding future infrastructure dependencies, and specifically, they mentioned that we were using a lot of uncertain technologies. Now, with this critique, we found it a bit confusing because if we look at the scope of things, everyone is using uncertain technologies. There's no team that's using that has like completely tested technologies, from the reactors, from the pressurized rovers. Everyone is doing something that's out of the norm, something that hasn't been done before, and that's what makes a Mars manned mission exciting. But we do think that our team use technologies that we know exist today and that can be used for Mars missions. So weather CubeSats, they're not just there to increase mission complexity. They're not just there to just sit around and just do nothing. We need accurate weather monitoring because our landing site requires it. Jezero Crater has a lot of regional dust storms that can happen, and in any mission, crew safety is the number 1 priority. So we need a real-time continuous weather data for our astronauts to schedule their expeditions safely. And it's the same thing with the relay network. We need to be able to communicate with Earth. So the main habitat needs to have some sort of connection with the Mars relay network, which should have a connection with the Earth deep space network. Okay, so these are technologies that they're not from science fiction. They're not something that we designed manually. These are things that we see happening in the near future.
For some of the criticisms that Team Sol Elpis gave us, they had some questions about the autonomous setup on Mars, like how we were going to set up the entire thing. So for the questions regarding the autonomous infrastructure and the robot function uncertainty, we assume that the question was referencing, obviously, the preparation of the habitat. And it's important for us to emphasize that the autonomous process is employed as a tool where it can increase mission efficiency, but ultimately should not be the difference between crew's life and death. And even though the automation process will be extensively tested before its implementation, the design does not make this an issue for human survival. So regarding the questions of like if the designs like fail, like if the robots fail, like if there is any serious robotic or logistic issues, the mission plan is flexible and capable of modification. And since the arrival of the crew on Mars is not dependent on the readiness of the habitat, there are manual ways to set it up, and there is life support for the crew to sustain them until the mission settlement is built. So if the robots fail because they're only used for efficiency and isn't like the primary function of it, the astronauts and the crew can set it up themselves. And it will set back the mission plan, but it's capable of modification, obviously. And to specify the usage of automation for the setup phase, the robots will be used for setting up the inflatable habitat, gather regolith to use for radiation shielding, and the spider robots will assist in the setting up for the power systems. Team Sol Elpis also asked us to talk about our nuclear reactor power source. So this is like a little bit more that we said in our report and stuff. So in order to provide an expandable infrastructure on the surface of Mars, we have planned to use nuclear fission, the use of nuclear fission using kilopower nuclear generators under the NASA Fission Surface Power Program. A system is entirely independent of sunlight and Mars dust storms and uses passive sodium heat pipes for transferring the heat generated by a cast uranium-235 reactor core into Stirling engines. For supporting our 5-person crew, 1 to 4 such generators will be deployed autonomously with the help of the Rocky Spider bots, as we said before, with each generator producing between 10 kilowatts and 40 kilowatts, depending upon the technological advancement.
And now for Team DexLab 1. So actually, the DexLab 1 team just wanted clarification on our methane fuel production, from what I understood. So also we would like to thank them for acknowledging the fact that our team took into account the fact that the MOXIE system on the Perseverance rover obviously needs to be so much larger for a Mars manned mission. So this is something that we took into account, and they noticed that. So for the methane fuel production, I don't know if we didn't explain that correctly in our presentation, but we're using the Sabatier reactor to produce methane and also to produce water. We're technically using 2 ways to make water. So we have the water processor assembly and the urine processor assembly, along with the Sabatier reactor. So we inserted like a little schematic for that. So we obviously capture the CO2 and the H2, and then methane and water are produced, and the water electrolysis produces more hydrogen in a closed loop, and we have methane as fuel. And this is just the MOXIE functional block diagram for extra clarification. But I think this was just a misunderstanding, not really a strong critique.
And finally, for DexLab 3, we wanted to clarify a little bit about what you said about how we cannot get liquid water because there is no liquid water on Mars. We want to say we are well aware of this. It was just kind of like a phrasing error, I suppose. We have provided the crew with equipment to drill and extract the liquid water by melting the ice beneath the surface. And we apologize for not explaining this explicitly in our presentation.
Thank you, everyone, and we hope we wish everyone good luck.
You can see the presentation?
Yes, go ahead.
Okay, perfect. Well, guys, today we're going to present our defense session. And first of all, we would like to thank everyone for taking the time to evaluate our project and providing feedback in the critique session. We truly appreciate every observation because it gives us the opportunity to explain our engineering decisions in greater detail and clarify aspects of our mission that may not have been fully addressed during our presentation. So today, Mission Acutis will respond to 3 observations that were raised during the critique session. These observations are from AI Suspect, LavaTubes, and the image selection. So we believe that the engineering project should be evaluated based on their technical design, scientific justification, and supporting documentation. Therefore, through this defense, we will address each observation individually and provide the evidence behind our decisions. So, to start, we have the first observation. During the day 2 critique session, though HiveMars mission suggests that part of a mission acutis may have been generated using artificial intelligence. This observation appeared to be based on the visual design of several presentation slides on the result of an AI detector indicating approximately 54% AI probability. We respectfully disagree with this conclusion. A visual style or a probabilistic AI detector result does not constitute reliable evidence that content was generated using IA. The slides in questions were created from an official editable Canva template, which was later customized by our team through modification to the layout, colors, graphics, and content to reflect our mission. The similarity identified by the detector is therefore a consequence of using a common presentation template, not of AI-generated work. Furthermore, our complete mission report documents the engineering process, technical decisions, calculation, and design methodology deployment by our team. The presentation was a simply and visual summary of that work. For this reason, we believe that our project should be evaluated based on the technical content, engineering justification, and supporting documentation rather than all the appearance of presentation slides or the output of a probabilistic AI detection. With this clarification made, we will now continue with the remaining observations and demonstrate the engineering principles behind our missions.
Also, to clarify, we made 2 videos that this first one you are seeing that we are space them illustration that were already part of the database Canva. This is important because the question slides will not generate we select and later added of formation in an educational program, which is gives the template we use is one of the resources able through access. In this second video, shows our final presentation opening directly in Canva. In this video, we demonstrate that the slides can be edited manually, including the text, images, layouts, and visually elements. This shows that our team customized the template to fit our own mission content rather than using AI to generate the presentation. Together, these videos demonstrate that the similarity in visual style comes from the Canva template, not from AI-generated content.
Okay, so since the start of the contest, the AI have been clearly provided, and all agree on that part. So I'm going to read the exact words that the team told us. As a result of AI detection, technology is not being perfect. We request for anything which has been suspected of AI to provide sources to images as well as the making process of the slides. Well, we clearly see on the underrated paragraph that they say that the AI detection technologies, they are not perfect. So we decided to use the same AI detection on images and another one to prove that we didn't use AI on the generator.
Okay, to respond to that criticism, we tested the same AI detector with screenshots taken directly from the YouTube video we use as reference. As you can see, the detector gave different results. One screenshot was classified as 71% real, while another screenshot from the same type of source was classified as 29% of possibility of AI. The only thing that changed was the screenshot, not a source. This shows that the detector is not always consistent. Because of that, we do not think an AI detector is enough to prove whether a presentation was made with AI. It should only be one tool, not the final proof.
And just to clarify, and we can see in the second picture that the page says this image is likely real, 20% real. In the next paragraph, we can see that they say AI likelihood. The 20% real is the percent of AI that could be on the image.
Now we also took screenshots straight from our presentation, and the results were very different. As we can see, one of the sources says that is 97% real, and the other says is just 4% AI. This is weird because the screenshots we took straight from YouTube had different results. So it is kind of weird there. Next slide, please. We can see the same thing with this next slide. As we can see, 96% real and 4% AI likelihood. This shows us that maybe AI detectors are not that fiable, not that good at detecting if an image is real or AI. So this shows us that maybe the YouTube screenshots may be modified by some kind of other AI or anything, because with the screenshots straight from our presentation, the results were that they had even less AI than the screenshots from YouTube. Now following with the next part.
Well, in the next part, we will talk about the critics about our lava tube proposal. Well, we have to remember that radiation is the single greatest threat to human survival on Mars. Galactic cosmic rays, commonly referred as JCR, bombard the surface constantly. Solar flares can deliver lethal doses in hours. Our team solution is both physically sound and operational intelligent. A 50-centimeter wire shield supported by a strategic deployment system. Let me explain the physics first. What is nature's best radiation shield? Because of hydrogen. Each wire molecule has two hydrogen atoms. When a high energy particle hits an hydrogen proton, it's an equal mass collision. The incoming particle transfers nearly all its kinetic energy in a single hit. The neutron slows, the proton recoils, and the energy dissipates as harmless heat. The hydrogen is nature's best neutron moderator. Now, 50 centimeters. That's 50 grams per square centimeter. For heavy ions, this thickness forces continuous collisions, each one draining energy until the particle slows or stops. For solar energy particles, 50 centimeters reduces over 90%. And for CGRs, it cuts the dose by 60 to 70%. Not perfect, but enough to keep astronauts within safe career limits for a full mission. Wire doesn't block radiation like a wall. It slows, scatters, and absorbs through hydrogen collisions. 50 centimeters give you one of the best stopping power per kilogram of mass. That's why 50 centimeters of wire is the matter wire of shield on our base. But a shield is only as good as its deployment. Our team uses a bridgehead strategy. Before any crew lands, we send autonomous drones and robots to verify the terrain. They assess ground stability, subsurface ice content, and radiation profiles. This ensures we land in a location with optimal resources for water extraction. And here's the operational advantages. Our base is fully foldable, deployable, reconfigurable, and modular. Because it's not fixed to a permanent foundation, we are not locked in to a single location. If the bridgehead robots identify a better spot for ice extraction or safer radiation conditions, we reposition. Our base go where the resources are. This is how we integrate physics and strategy. 50 centimeters of wire for radiation protection, exerted in situ, deployed on unverified terrain, and positioned with full flexibility. So now we continue with the next critic.
Well, first of all, we would like to thank DeskLab1 for their observation. We genuinely appreciate every question, as I mentioned at the beginning of the presentation. So after review the comment, we believe the observation refers primarily to the visual representation shown on one of our slides, rather than to the engineering concept itself. The criticism focused on the appearance of the drilling machine used as an illustration, not on the technical architecture or operational role of the drilling system within our mission. The images, was intentionally used as a simple visual analogy to help the audience understand the function of the head exploration system. It was never intended to represent the exact machine that will be deployed on Mars. Given the limited presentation time, our priority was to explain the engineering process instead of presenting detailed renderings of every subsystem. So we can say that these images was also our error. To continue, from an engineering perspective, however, our proposal clearly includes a robotic drill system. In sections 2.1.3, Robot Resort Assessment, we describe how this system performs shallow subsurface drilling to recover geological core samples. These samples are analyzed to determine ice content, mineral composition, and soil properties. This information is essential for validating the landing site, planning future water extraction, and supporting our in situ resource utilization strategy. The drilling system is also integrated into section 2.2.1, initial deployment, before the habitat is installed. The bridgehead exploration system surveys the selected lava tube using ground penetration radar, LiDAR, high-resolution cameras, and robotic drilling, as I mentioned um, in the last presentation of our mission. These technologies work together to verify structural stability, accessible dimension, subsurface ice distribution, and safe habitat and structural instability. Conditions before construction begins. Therefore, the drilling system is not an insulated tool. It is an essential component of our engineering validation process and plays as a critical role in reducing operational risk before astronauts occupy the habitat. This approach is also consistent with current planetary exploration technologies. NASA's Perseverance rovers use a robotic drill to collect geological core samples on Mars. The European Space Agency Rosalind Franklin rover was specifically designed to drill up to 2 meters below the Martian subsurface in search of water and potential biosignatures. Likewise, NASA developed the Trident drill for the Viper lunar mission to investigate subsurface ice. These missions demonstrate that robotic drilling is already a proven technology for planetary exploration, and our proposal follows the same engineering philosophy by integrating robotic drilling with remote sensing technologies before the habitat deployment. For this reason, we believe the engineering concept should be evaluated based on the documented design and its operational function, rather than on the illustrative image used during the presentation. The concept itself is clearly described, technically justified, and integrated into multiple stages of our mission architecture. If we had the opportunity to improve the presentation, we could certainly replace the illustrative image with a rendering of a planetary robotic drill, such as NASA Trident system, or the ExoMars drilling mechanisms. That will improve the visual accuracy of the slide. However, this change will only affect the illustration, not the engineering design, because the robotic drilling system was already fully defined and integrated through our proposal. Thank you once again for your time and attention. We sincerely hope that today's defense has demonstrated that Mission Acutis is a result of careful engineering analysis, technical resonancing, and dedicated work of our entire team. We appreciate the opportunity to clarify our project, and we thank everyone for listening.
Thank you so much for your presentation. Great job. Is Team Orion here to present?
Hi.
Hello. We will start in about a minute and a half. How does that sound?
Yeah, that's what's yeah,
Okay.
fine.
Go ahead.
The final drawing. The estimate weight of Orion is components is the weight are based on similar NASA rovers and engineering estimates. Orion 100 kilograms. Lander structure 12K. Each V-bar is 18. The tools each 5 to 10 kilos. Total 250. No. Notes. These are estimated weights.
We add a clear space explanation and diagram showing how Orion transformed from a lander into a rover. 1. Landing, 2. Panels open, 3. Wells deployed, 4. Robot arms extended, 5. Tools unlocked, 6. System activate, and 7. Mission begins.
The tentacles specifications let rover 3.5 m, the width 2.7, the height 2 m. The weight of the rover is 9,000 kilograms. The weight of the lander is 200 kilograms.
Payload capacity is 2,000 kilograms. Max speed 0.5. Wheels 6 independent suspension. Power sources, solar panels, and batteries. Operating temperatures minus 100,000 to
20 C.
Communication high gain antenna, autonomy semi-autonomous systems.
Orion. The transformation process of process is one of the most exciting parts of our design. When the spacecraft launches from Earth, it remains compact travel
configuration. These shapes reduce weight, save fuel, and ensure maximum efficiency during the journey. After arriving at the mission destination and safely landing, the transformation process begins large spindle sections slowly come down from the side of the spacecraft. These sections are carefully engineered to create additional rooms and workspace. Once fully expanded, the spacecraft becomes significantly larger than its original launch site. The transformation creates separate areas for sleeping, working, exercising, eating, and conducting scientific experiments. The habit includes private sleeping quarters for crew members, scientific laboratories, storage components, exercise facilities, community center, dining and kitchen areas, medical stations, mission planning workspace. The modular designs allow the habitat to grow without requiring multiple launchers or additional constructions. Everything needed for the mission travels together inside one spacecraft. This transformation makes that spacecraft feel less like a cramped vehicle and more like a small, fully functioning home and stretch station. Life during a 1.5 years mission can be changing. Astronauts must stay specifically health, mentally focused, and emotionally support while living far from Earth. Our habits are is designed to meet all of these needs. The sleeping quarter provides personal space where astronauts can rest and recharge after a long workday. Having private areas helps to reduce stress and improve mental well-being. The kitchen and dining sections allows crew members to prepare and enjoy meals together. Shared meals help maintain morale and create a sense of community among the crew. The stretches laboratories are equipped for science experiments related to biology, chemistry, engineering, and space exploration. These labs allow astronauts to continue making discoveries through the mission and exercising in areas specific important because living and reducing gravity can weaken muscles and bones. The tread miles machines and exercising bikes help the astronauts stay healthy and strong. These habits are include entertainment and relaxation space where crew members can read, watch movies, communicate with their loved ones, or participate in recreational activities. By improving both workspace and living space, our design creates an environment that supports the crew physical and emotional health through the entire mission. A mission lasting 1.5 years requires reliable life support system. Our habits include advanced technology that helps astronauts survive and thrive while discovering reliable sources in the air recycle system continuously filters and cleans the air, removing carbon dioxide and supplies of fresh oxygen. This reduces and constant resupplies emission from air. The water recycle system captures and purifies used water, allowing it to be used more. This technology greatly reduces the amount of water that must be carried on board. Solar panels provide renewable energy to power equipment, lighting, computers, and life support systems. Battery backup systems ensure that critical operations
continue even during emergencies. Radical shielding helps prevent astronauts from harmful space radiation. Strong
exterior materials provide layers in press crew safety during a long periods away from Earth. Emergency systems are also built into the habitat. Medical equipment, backup communication systems, emergency shelters. Our fire suppression systems help prepare the crew for
unexpected situations together. These systems create a continuity and security environment that allows astronauts and agents to focus on the mission rather than worrying about the basic survival. Our, our Transformer Space Habits represents a new way of thinking space exploration by combining transportation and house into a single design where we eliminate where we make the spare habits, reducing overall mission costs. Inspiring by
Mr.
Harvard Harmony.
Innovation. The versatility of a RB and the adaptability of transformers will create a solution that is practical, innovative, and exciting. The spacecraft begins its journey as a compact vehicle cap- capable
Capable of traveling through the space vigorously. Once it reaches the destination, the transformer into
spacious habitat complete with living quarters, laboratories, exercise facilities, communication centers, and life support systems. This design provides astronauts and agents with everything they need to live, work, and conduct research for 1.5 years. It supports their physical health, mental well-being, and size goals while maximizing efficiency and sustainability. Most importantly, it gives the crew something every explorer needs a space to call home. If I were an astronaut, I would absolutely want to live in this habitat. It is safe, comfortable, innovative, and designed for the future of space exploration.
with this transformer spacecraft, astronauts wouldn't just travel among the stars; they would live among us. Robot system power system. Portable solar panels, recharging batteries, store energy for the night operation. Mobility system, six-wheel design, moves over the rocks and sand, stands on uneven terrain.
Robotic arm system. Two robotics arms used in travel tools help build habitats and collect samples.
Storage system, carry seats, stores tools, hold space parts, protect supplies from dust. Community system, leads data onto Earth communication with e-bots, use cameras and antennas. The navigation system, camera scans the terrain,
Detects vehicles choose safe routes. IA systems work without constant control, chose the right tool, complex tasks step by step. VBot systems work with 3 VBots: inspection, materials transport, soil analysis. Safety systems detects problems, protects important systems, send warnings if needed.
Habitat construction process. Orion arrives at the landing site and scans the area. Orion transports the habitat part using its tools and storage. Orion uses robotic arms to assemble habitat pieces. Orion sets up power system, the solar panels, and batteries. Orion checks the structure and makes sure it's safe. The habitat is ready for future astronauts. Orion carries seeds and materials needed to start small greenhouses before the astronauts arrive. Robot repairs the area and makes sure everything is ready for the future crops. This helps reduce amount of food
What needs to be brown from here. Harry sees Orion prepares the greenhouse. Orion checks the temperature. Orion monitors water and protects the growing area. Why you need to choose Orion? Because we have the challenges, and when the through the terrain, six wall suspension system allows Orion to move safely on rocks, sand, and steps. Radiation.
Radiation. The electronics are protected inside the roll over radiation levels that constantly monitored.
Low temperatures.
Its all components are batteries designed to work in cold conditions.
Astronauts. Orion prepares the landing site, builds the first habitat, and step up power before the humans arrive. Limits resource. Orion carries tools and stretch for water, ice, and local materials. What we need to bring form. Working alone. These robots help with inspections, transporting materials, and collecting samples. That's all for my group. Thank you.
Thank you so much. And I believe the next team is Olympus. Are you in the room?
Yes.
Are you ready? Okay, so there's 2 Noahs. So Noah Doden, it's your team's turn now if you'd like to present.
Okay.
And you have some feedback.
Yes. I'll share my screen.
Okay. And Noah C, Noah Column, you're next after this. Go ahead, you have 20 minutes.
Okay. So we have some responses to some critiques.
Can I pause you for a second? You have a lot of feedback, so I don't know if you guys have two computers on. If you do, mute one of them completely.
Okay. So yeah, we have some responses to some of the critiques from Wednesday. First, Dex Lab and asked us if we could be specific about the mass of our energy production and the purpose of the egg chickens. So the energy production, the solar panels can increase solar energy production per day would be between 187 mg/m2 and 3 mg/m2. Weight 22 panels times 18 kilograms equals 396. Nuclear power, we are using kilo power, which is small nuclear reactors that create anywhere from 1 to 10 kilowatts of power and weigh up to 1 ton, to weigh from 1 ton to 1.5 tons. The objective of our purposed experiment is not to establish a farm on Mars. Rather, we want to use this technology as a biological model to investigate how reduced gravity and space radiation affect the development of a living organism. The knowledge gained from this experiment could improve our understanding of how low gravity and radiation influence biological development and physiology. These findings would contribute to future human space exploration by providing effects of long-term exposure to extraterrestrial environments on the human body and helping to develop strategies to protect astronauts' health during future missions to the moon, Mars, and beyond. Next. Red Frontier asked how we would fit the large inflatable habitat inside of a lava tube without breaking it. First of all, the habitat will be based in two parts. One part will be above the lava tube, and we will situate the other part below. Now how we are going to get a base at the bottom by means of pulleys using a rover. The vehicles we have, we're going to carefully lower the inflatable once it's at the bottom. It's inflated, sent to the 3D printer, coated, and that's it. They asked how would the structural stability of the tube be verified before crew occupation. For the verification process, we will use the Boston Dynamics dual-axle robots. These robots are designed to explore areas that would be inaccessible, such as craters and lava tubes. These robots will have integrated TLS and MM sensors. These robots will also be used for unstable or collapsed sections. While the robots collect the data, it will be processed using specialized software to create an exact digital twin to know each section. Next. Actis mission. The landing site of the mission will target the Tharsis volcanic province, a site confirmed to have subterranean lava tubes. Water frost forms on the volcanic summits, providing a key resource. Life. Underground lava tubes shield against radiation, making them prime spots to find microbial life. Mission objective. The primary objective of the Olympus mission is to establish a safe, sustainable human presence on Mars by targeting the Tharsis volcanic province. Scientific goal. Speleology and planetary geology map, scan, and explore Martian lava tubes to understand their morphology, access structures, stability, and search for subsurface water, ice resources. Astrobiology. analyze gathered subterranean dust and rock core samples to look for signs of past or current microbial life. Sheltered from harsh surface radiation, biological development models use colossal biosciences synthetic artificial egg membrane to hatch fertile chicken embryos on Mars. This serves as a biological model to observe how reduced Martian gravity and cosmic radiation affect the cellular growth and physiological development. Next. Actis mission also asked design justification. Inflatables save launch weight, while a 5-centimeter 3D printed outer shell blocks radiation and extreme weather using local materials. Vertical layout. Multi-floor layouts break up psychological monotony and confined stress, forcing social interactions through shared pathways. That is all.
That's everything?
Yeah.
Okay, thank you, team. Noah C., if you are ready to defend your mission.
Yes, I didn't make any slideshow or anything, so
That's okay. Everyone is applauding you for doing this project on your own, so we're all proud of you for handling that. So just go ahead with your defense.
Thank you. So one of the teams asked or accused me of not having the perfect weight. And that's really hard to get whenever you don't have access to all of NASA's weight charts. But I did what I could, and I spent a ton of time on the NASA website. Whatever I couldn't find, I looked up on Wikipedia. That's it. Mine was pretty quick. I only had one person accusing me. I think so.
Okay, is that the end of your presentation?
Thank you, guys. Mine was fast.
It's okay. It's okay. I'm glad you were all here today, and I want you to know that I'm so proud of all of your hard work. You guys did a lot. It's incredible the amount of work every team did. And I just want to mention, no humans have stepped foot on Mars. So everything you're doing is helping us get towards that goal. And the lengths you all went to, the research you did, the thinking that you did, it's wonderful, and it makes me so excited for the future. And I appreciate all of you. Every single one of you have done a great, great job. And it's going to take, because I have 17 25-page papers, it's going to take some time to get those graded with the judges and the panel and everything. So please give me at least 2 weeks. It may be 4 weeks. If you don't hear from me, just be patient because it takes a long time. There will be first place overall, first, second, and third place overall, and there will be a first place for human operations, a first place for engineering, and a first place for science. And everyone will get a PDF of your certificate for either participation or if you were first, second, or third place. So please be patient. There will be a major announcement on our social media and on our website, and I will email you all of the information when everything is graded. So give me 2 to 4 weeks to get all of that complete. Does anybody have any questions for me? Go ahead, Hadi.
Yes, so in the team names that you mentioned, you still have the old name of the other Hadi in the team. I'm Hadi Harfoush. The other Hadi in the team, he worked with us for approximately 6 days and then ghosted the team. So we don't really want him getting a certificate because he literally said, I'm just here to get the certificate, and ghosted us and didn't really do any work.
And which team is that? I'm looking at the list just to make it quicker.
DexLab 1.
DexLab 1. Okay. I will remove him. Okay, so you guys ended up with 4 people?
Yes.
Okay, thank you for letting me know. I appreciate that.
Yeah.
Anything else? Okay, everyone. Great job, and I appreciate all of you. Have a wonderful summer. Bye-bye.